Morning, everyone. On behalf of the ISO, I'd like to welcome you to today's Resource Adequacy Modeling and Program Design Workshop to discuss midterm and long-term study results, year-ahead study update. My name is Christina Guimera, representing ISO Stakeholder Affairs, and I'll be facilitating today's meeting. Today's slide deck presentation is available on the initiative webpage, and you can get to that page by going to kaiso.com, and then under the Stakeholder Center tab, on the homepage, you'll see policy initiatives. If you click that link, it'll take you to our main initiative landing page where you can search for the initiative webpage. Today, Aditya will take us through on introduction stakeholder feedback. Afterwards, Mark will give us proposed updates to the year ahead inputs and assumptions. Afterwards, we'll review midterm and long-term study results with Aditya. Following lunch, we'll hear on expert presentations on PRM and QC considerations with representatives from NP Energy, Astrape Consulting, E3, and CPUC-ED. Afterwards, Aditya will wrap us up on next steps before we adjourn. This meeting is being recorded and the video file will be posted on the initiative webpage for information and convenience purposes only. The recordings and any related transcriptions should not be reprinted without the ISO's permission. If you need any technical assistance at any point during the meeting, please send a chat to Inteller Events. To ask questions during the meeting, you can open the participant and chat panels on the bottom right. You can then raise your hand. If you're joining audio only, please press *3 on your device. For everyone joining us today, please make sure to state your name and affiliation first before speaking. And you may also send comments and questions via chat to all panelists. And with that, I'll turn it over to Aditya. Yeah, you can do that.
Hi, good morning, everyone. Welcome to the, standing in the wrong location here. I'm hiding myself. All right. First of all, thank you very much for all your feedback and input to the first workshop that we had in October. Much appreciated. And thank you for keeping the comments and input brief, so it was really easy to process and incorporate into the next round of discussions here. It might require us to think a little differently today versus yesterday. Yesterday's focus was what kind of RA process changes we should do at the ISO to improve visibility, to figure out backstop, and all the other discussions that we had. Today's focus, even though we may use similar terms from yesterday, is directed towards what default counting rules and what default planning reserve margin should be used. So when we use UCAP yesterday, the reference and context is a little different than when you talk UCAP in the default counting rule space. So wanted to mention that upfront. And we are in that proposal development zone of the broad category. We don't have, we will come up with the straw proposal like Ansel mentioned yesterday in 3-4 months, but this is all in preparation in track 1 to help that. Track 1 is the modeling, the default rules, and ambient D-rate and that kind of stuff, UCAP. Repeat in a sense of what track 1, track 2, and track 3 are doing. We are going through the modeling process here, as I mentioned. The discussion will be on default counting rules, accreditation methods that we should be focusing on, thinking about. We have 4 expert presenters giving us views from across the country for us to think about, and various methods that we could employ. We also have UCAP design. Again, UCAP from a default counting rule perspective, how do we address UCAP? What factors should go in that calculation of forced outage rates and stuff? So this UCAP will be different than yesterday's conversation of UCAP. And track 2 and 3 are the different tracks. As Christina mentioned, what are we going to do? We will do a quick stakeholder feedback and KAISO response to that, and Mark will talk about the updates and changes to the year ahead as inputs and assumptions. If you remember last time when we presented, we said those October workshop results were draft results, using summer assessment assumptions. So we walked through the various assumptions that we've used, and we've received feedback. We're making adjustments to that, and then we will rerun the model, and that model and finally calibrated 0.1 portfolio will then be used to come up with the default planning reserve margin number. And we also have worked with Astrape Consulting. Kevin is here to present the results from midterm and long-term study results. One of the things that we mentioned earlier was we want to focus resource adequacy planning and assessment across the next 10 years, right? So we talked about year ahead being 2025, and the next 3 years is to assess if the authorized procurement levels are sufficient and what does that LOLE portfolio, LOLE is be from that resultant portfolio, and then the long term was trying to look at LSE plans. So we've Kevin and his team has built all the models, and with those models, we have results from midterm and long-term analysis. So we can look at how the risk profile changes through time and other information that comes out of that. And we have presentations from industry experts that discuss QC considerations that we can think about. And we can then calculate planning reserve margin based off of that and next steps from a high-level timeline. All right. The stakeholder feedback was overall positive. And thank you so much. And we've received a good number of suggestions to improve the modeling framework. Our assumptions were used year over year in summer assessment, but we've had a lot of one-off conversations over time, but never a full stakeholder discussion at that level of detail that we had. So we've received a good amount of input in that space. I'll try to keep it brief and also touch all the various themes of input we've received. The very first one was general support. Thank you. The second one was there was a request to clarify discrepancies between CPUC and KAISO modeling. CPUC also models the in their RA proceedings, future LOLE work, and there was a request to show comparisons of assumption differences and methodology differences. That is in development. We will bring it to you guys next week. There was an ask for counting rule alignment between KAISO and CPUC. That is something that we will have to explore with all of you in this workshops, right? Because CPUC's approach is a 24-hour approach. Ours has historically been a peak hour focused approach. So as we change our default rules, do we want to have a default rule for a 24-hour period and things like that? That kind of determines the approach we go there. The next comment was a request to develop a shared data set between KAISO, PUC, and the Energy Commission. That is in discussion because what happens is when you're trying to build a KAISO-wide model with all the data, and then you need future information, you have to collect it from various entities. Who is the owner? Who does the survey? What is the level of granularity needed? It's a huge effort. So we're trying to figure out how it can be done. And like I said, early this year, when I came requesting for a survey of all your LSE data, I told that'll be the last time we will do, and we will coordinate better, and that is still in motion. You can stop me anytime with questions. I just wanted to mention that. There was a question around load, solar, wind, and weather profiles, improve and incorporate correlation between them. We will talk about that in the slide deck, so I'll not talk in detail, but a key highlight is the KAISO's methodology preserves the correlation in the base portfolio, base profile, and then that base profile is perturbed 500 times in different ways to come up with random profiles for each of these things. So you still have your base production profile that is adjusted. The incorporation is kind of hard, but we can look at correlation with incorporation with weather is kind of hard, but we can look at that correlation chart later this morning. And a reminder that CEC is also in development of stochastic profiles for load. That will be used consistently. That's the idea for all the three entities to use the same set of stochastic set in future modeling. Use newer outage data because our outage dates are outdated. Yes, we are planning to do that. Obviously, like you know, we have multiple systems, GADs, which we don't have access to. We have the OMS data, and in CEDA, we have some information for shown RA resources. So there's multiple sources we are trying to figure out how to get that latest data and how far do we have to go back in calculating this. So we'll have a brief conversation around that and request stakeholder feedback in what outages, what classifications, categories should be used, and how far do we go back into that. Hydro year sensitivity analysis was requested. Hydro is a variable that we've always modeled as an average hydro for any long-term assessment, but anytime we did a summer assessment, because we would have information by Feb, March on the known summer conditions, so we were modeling the known hydro profiles for that current year in summer assessment, but when we came to long-term modeling, it was always average. Stakeholders have requested to make that also a stochastic variable. We have a high-level approach that we will propose today on how to look at hydro stochastically. The next question is around storage modeling improvements, dispatch strategy, duration, round-trip efficiency. There was questions around some of those resources are 3 hours, 2 hours, 1 hour, 5 hours, 6 hours. So we don't have good information, but based on whatever information we were able to look at, we did pull up that information. We will discuss that. We are moving to a new version of Plexus. Hopefully we'll be able to accomplish all of that in the next 2 months, which allows battery resources to be individually modeled. So then we will be able to model their own characteristics, their own profiles and stuff. That testing is in progress. Couple of stakeholders have asked to continue performing scenarios 1 and 2 for sensitivity analysis from a backcast standpoint. The intent of running those analysis this year was to show the level of reliability that is achieved if you only relied on what is shown to the ISO. And it requires a ton of assumptions. When you do an historical assessment, it's a lot of work. And I'm still struggling to see the value of a backcast analysis when we are able to show that the level of shown resources are not necessarily sufficient, and we rely on other resources too. So that is something that we will still continue to think, but the next thought was including 2025 year ahead showings to update the analysis. The year ahead showings are also only for 90% for the summer months. So we still have to make assumptions for that remaining 10%. Yeah, it's as good as whenever you have to make assumptions, it's as good as what we currently have. So we don't intend to perform the analysis. There was a thought on how we model imports. We have 5,500 megawatt import limit. There was discussions around that should be a shaped import constraint requirements. You have to have resource specific and non-resource specific imports. When you don't have really good long-term resource-specific contract information, it kind of becomes hard to model that shaped import constraint. But we can perform a range of sensitivities to kind of show if that is how much can you rely on 4,000, 3,000, 2,000, if that will be useful in the analysis. The last thought was increasing granularity of import regions instead of one VEC non-CAISO bubble. We are looking at data availability and data quality. The VEC data anchor data set is good for the near term. Excuse me. So we are trying to see if that can be modeled and then what the runtime implications are and stuff. So that might be a future potential improvement, but for right now, we're working to improve hydro, storage, representation, and modeling, and the imports discussion. All right, so that. I think that wraps up the themes of feedback we've received and our high-level responses to some of them. Obviously, there is more feedback that we are looking through. I see some questions in the room. Noah?
Good morning. Noah Tom from Middleware Power. We made a suggestion to do a backcast based on the 2024 month-ahead showings. That does not seem to be captured here. Can we talk about that for a sec? And I recognizing the fact that you said you don't, to which I don't understand why, but you don't find value in doing such a backcast.
Yeah, the backcast comment was the first one. Kind of looped it together. I should have added there. You guys is over there too. The 2024 system was operated with resources that were given, right, based on the conditions that we've had at that time. So whatever was shown was shown. I'm struggling to see the value of doing a historical backcast analysis and what it will actually do, because we know the answer. The lights were kept on, so.
No, that's not the answer.
Then.
I mean, just because the lights were kept on doesn't give you a what LOLE you had.
So the future cast scenario 1 and 2 kind of showed that it is not a 0.1 portfolio. So
the future cast is some hypothetical portfolio that's not based on procurement of what was shown. So I'm still trying to get to just because we haven't had a blackout in 20 years must mean that the system's okay, but yet, you know, we had a blackout in 2020. Well, sure, let's change, but we haven't had any since then. Well, is anything broken? I mean, is that the right question to ask?
So let's see, we ran the analysis for 24. Can you walk me through what's next after that?
Yeah, sure. I think it would be, I think that analysis would replace maybe scenario 1 and 2, maybe 2 primarily, but it would help benchmark where the program in aggregate is for our system. And then I think 3A or 3 and 3A, where the ISO had for where do we need to be, would give a better sample of what, you know, where LRAs need to be based on various counting conventions and so forth to ensure that we have a reliable system. At least you know sort of for certain in 24 how it was, maybe even 23 how it was, and how do we get And what would it take to get to 8.1, which is what 3A probably with more stress testing would end up doing.
Yeah, Kevin Card from Astrape, just offer a couple of observations on various calibration efforts. So, I mean, calibration is not just about whether the model predicted loss of load or not, and did we have it or not. It's also, there are lots of other metrics, calculating or calibrating the level of surplus that you had, even things like market prices, activation of emergency operating procedures. I do think that there's value in that calibration to make sure the models are picking up the distributions. And so you can do different levels of calibration, whether you incorporate the actual outage history. You can do the calibration with the sampling of stochastic profiles still, or the actual renewable profiles in. I do think that there's we see a lot of value in working with this for a lot of our other customers in this calibration exercise of informing how we set up our future runs based on the backcasting that we do with the prior.
We have an online hand raised by Perry.
Perry?
Hey, this is Perry Servideo, CISA. I just wanted to echo Noah's comments about the importance of doing essentially the backcast with the real data that we've received from the monthly plans. He described why, it's good to do that to benchmark, and Kevin also described that. But I had just another thing to add that you might find value in doing it, because as you know, whenever you go forward and you're doing next year, the year after, et cetera, you're always going to have to make some assumptions for next year. So at least if you have a rolling backcast of what actually happened in the past year, you could use that information to help tune your assumptions going forward. Just wanted to add that, and say that we would support you doing an actual study for the prior year based on the real data that you received. Thank you.
Thank you.
And next we have Steve.
Steve Keen from Edison. Just the same sort of thing. We've asked before to have a backcast for exactly those reasons, because it would give us a level set. We know how things have turned out the last couple of years, but if we knew kind of what last year was like and what we expected the LOLE to be, it would give us an idea of how are we doing with that, because I don't think a lot of us have a good idea, even if we get to a 1%, a 0.1 LOLE, what does that mean? And I think just, looking at last summer, which was, not really too stressed, and if we saw what the LOLE was that we had going into it, I think that would allow us to kind of provide a lot of information as to where we are and what we should be looking at.
Thank you. So is the idea that only model shown capacity by month in a backcast, but not model any other resources?
Yeah, I mean, that's generally the purpose of the RA program, is set a requirement for LSCs to procure to, so that the ISO has a basket of goods to manage the system.
Right, thank you. Any other thoughts? Yes, sir.
Yeah, Doug Karpa, Peninsula Clean Energy. I think I'd throw my support in along with all the other comments. It does seem like pretty good practice. I think the comments that Kevin had in particular, it's a useful diagnostic process too. Like if there's something that's critically wrong in the model that will like throw off screwy results, that kind of truthing is kind of the only way to diagnose it.
Okay.
So it's like if you do that and then all of a sudden the market prices or levels of imports or whatever turn out to be totally, utterly different from what actually happened, you're like, we've got some pieces of this to look at. So that sounds like a worthwhile exercise.
So now I'm brainstorming in real time, which is always a bad idea, but is it a good place in the summer assessment report for next year to kind of say how the last year's was, so you have a backcast and 25 projection? Is that the assessment timeframe, or do you want it more in the RA space? Meaning, if you want to do an annual backcasting exercise, summer assessment sounds like a good house.
I'm currently not suggesting to do an annual backcast. I'm simply suggesting for purposes of ramped initiative that we should look at how we've done, and then what do we need to do to get to point one, which is what I think 3A with more stress testing would give us.
All right, we will explore that, and probably we should be able to do it, but all right, thank you. I don't want to commit to yes or no, but yeah, we will explore that.
We also have a hand raised by Kathleen.
Kathleen?
Thank you, Kathleen Colbert from Vistra. Can you hear me, Aditya?
Yes.
Excellent. I just wanted to add, I guess, one more thought for you to think about. I appreciate you taking this discussion back and thinking about it harder. And it's, you know, the stuff is complex, but I wanted to share with you our thoughts on this idea of backcast versus forward casting. And we've been very open about the fact that our primary interest is the forward-looking assessment. What resonated with me about this discussion came from Kevin, thank you, and Perry, also thank you, where I had my light bulb go off on the backcast value would be for tuning the assumptions that you're looking to include in the forward-looking assessment. I had been struggling with the value of it myself, to be honest, but I wanted to note that I heard something that might have contradicted that idea of that being the value in the group discussion. And so my flavor on this is whatever the methodology, like this set of resources that you're going to include in the forward-looking assessment, the value that I can see for the backcast would use the same set of resources. Does that make sense? At least what I'm saying, whether or not you agree, but as a basis.
Can you repeat the set of resources comment again, Kathleen?
Yeah. Yeah, so and I'll say it a little differently, is that if the purpose of the backcast is to calibrate the assumptions based on historical performance of the prior year, you would want to include the resources and the capacity assumptions that you intend to include in the forward-looking assessment. So if in the forward-looking assessment, you're only going to use shown, then you would backcast on shown. If in the forward-looking assessment, we're going to use a different variation of that, which is what I believe you're going to use, the backcast would be that full set to align and hold at least that element constant. Because if you change too much, then you're losing the value of the backcast to tune the assumptions on like outages and availability. That would be my concern, is if you change that core set of resources, the amount of capacity that you're assuming between the backcast and the forward-looking, I think you lose the value that I heard Kevin and Perry talk about.
Kathleen, one caveat to that is we already did a summer assessment that incorporated all resources are eligible energy only in the system. That is very similar to scenario 3A for expected resources in 24. And we did show a surplus of capacity to meet a 0.1 LOLE in that exercise. So what I understood Noah was highlighting was test the sufficiency of the RA shown capacity. And what gets shown is a function of the LRA RA requirements to do a backcast to do that. And second is to,
Oh no, I was going to say, I heard that as well. That's why I raised my hand. I don't see that as helping us get to improving the assumptions that you're using in the model.
This is Steve from Edison, and I think what Noah and I are trying to get at is if you do all the forward-looking stuff you're doing, you're making a guess as to what's going to show up as RA because you don't have a you don't have the full thing. What we're saying is for 2024, we now know what you were given for RA. We know exactly what you were given because everything's been in there. Use that and let's see what we got, for 2024. And then we can, look at that in comparison to how the grid actually performed. And we just think that that would be a good kind of a level set. If we end up that, okay, we didn't have a whole lot of problems in 2024, but the RA that we were getting showed us, I don't know, I'm just making a guess, like, 0.3 LOLE. Okay, that will provide some information. If it shows that it was a lot less than that, again, it would just give us kind of a level set, because I don't think when we're looking forward, you're always guessing about what sources are actually going to show up, especially with, it's hard to know what's going to show up for imports and all that. It's hard. What we're just saying is, let's just do one look with what we actually had and assume that that was what we had, because what we're saying is RA is what we think we need to make sure we're reliable. Let's just see, looking at what we had last for 24, does that meet the reliability criteria that we were looking for?
And I appreciate that, Steve, and I don't want to belabor it all. My intent here is to communicate to the CAISO that I don't share the view that you and Noah are articulating. However, I'm trying to see the value and articulate what value I see. And I just think it's important for the CAISO to hear the various stakeholder views. And the value I see is not about what's shown, it's about making sure that you're calibrating your hydro assumptions, you're calibrating the outage assumptions, as well as those for thermals, as well as for storage. That has value that I see. So if that's the intent, fully support it. But whether I think the value you are looking for, I just don't see a ton of value in. Thank you.
This is Kevin again from Astrape. I'll just offer a quick observation. So certainly, I think you need to have alignment between kind of the resource selection criteria in your backcast and future, but it doesn't mean that I can't have an alternate future case that has a different set of portfolio assumptions. Now, that aligned case allows us to benchmark, validate all the inputs, the stochastic profiles, the outage rates, market prices, other things. But I don't think it necessarily entails that you have to have that same consistent approach to setting the resources for the future official case. You just have to caveat, this is a difference between that. But in terms of doing the calibration, I agree that you do need that level of alignment. I don't know if that further muddied the waters or helped provide some clarification, but I mean, ultimately, a lot of our clients, we're doing the backcasts. That is a particular exercise to dial in the assumptions, understand the impact of all the inputs that we make. We need to do that against a future case that has similar setup, but we can still have future casts, future scenarios that have different set of assumptions, but we've still got this validation process in place that's allowed us to confirm a lot of the inputs that we have.
And I just one thing I wanted to add, when I'm talking about doing this, I don't know with Noah or anyone else, but what I'm thinking is, you don't use the actual output from the resources. You use the actual resources, but then you go through and do, exactly what you were thinking. You pick different hydro years, you pick different, you do the 500 different choices for outage rates and demand stuff and everything else. So that, basically it's the same thing you're doing looking forward. It's just you with an exact defined set of resources rather than having to guess, okay, this is what we see. These are the 90% that we see for the summer months. And here's all the other ones we're guessing will be there. You know exactly what it is. And I just, at least for me, it would help me understand exactly kind of, what the analysis, where the analysis is, what we're trying to do, I guess where the analysis is kind of coming out. Because I have a hard time understanding, I have a hard time when you come out and you say it's like a 0.3. Okay, yeah, on the one hand, I understand that. But on the other hand, I have a hard time really, understanding what it means. And I think just knowing like where we were for a year, like last year, it would just give me an idea of like, what does that mean?
Thank you. No, I still old. Okay. Any other comments, Christina?
Not seeing any other hands raised.
Yeah, thank you so much. Yeah, we will explore that thing. Now I don't even have an excuse of saying I don't have December showings. We should have December showings. So yeah, we'll go back and take a look at that. Sweet. All right, now I will pass it to Mark to walk us through the various year-ahead inputs and assumptions. You want to take from here? Okay.
I'm assuming that's just forward. Forgive me, I fought with the printer this morning, so I didn't print out my notes, and there's like 3 notes that I want to get right. So thank you. My name is Mark Kuchtra. I'm with the California Independent System Operator, and I'll be talking about our year-ahead inputs and assumptions, what we're proposing to change, what efforts we're undergoing for the change compared to what we presented on October 8th. So we're looking at these 5 changes and just some information to prepare, really information to continue the conversation. I'll talk a little bit about the energy resource modeling. We want to clarify a few things and make sure we're all on the same page from what came out of that. Some work we did on hydro modeling based off of comments we received and where we think we're heading from there. A little bit of a conversation about weather year alignment and what's in the model already with the stochastic profiles. The forced outage rates, which I think we all realize needs some updating and some attention, but that's kind of a big lift to do, and we want to make sure we do that right. And our loss of load events and reserve modeling to make sure we have kind of that conversation tied up well about this is how we're looking at what a loss of load event looks like and what reserves we're considering. And then we just also want to share some information about the differences between the 2024 and 2025 NQC list. I think we all know that they're different, but to put some eyes on that and see some pictures with it. For battery modeling, this is how we're currently modeling the resources for outages. We are modeling the outages as a D rate on both the charging and discharging, but it's not a uniform D rate. So what we're doing is breaking up those aggregated resources. So all the batteries in PG&E are flagged as PG&E in our bubble, or Bay and Valley. It's one battery resource. We break it up into 100 megawatt units. We apply a forced outage rate of 5.2%. And we run the same type of outage process that we run for our other generators to get that outage profile. And we turn that into a D rate across that whole aggregated unit. So if you look at our model from hour to hour, these are not the same D rates from hour to hour. It varies over time in the way that a forced outage rate would for a fleet of resources. It is aggregated again back into that larger profile. So that works together there. We did also take a look at the breakdown of energy storage durations. The vast majority of the storage currently on the system is 4-hour storage, about 8,600 megawatts, which is over 85% for when we pulled the data. About 700 megawatts are 5 hours, and then 600 megawatts captures the rest, which includes 1, 2, 3, and 6-hour storage. So we do average about 4 hours of energy storage. So that's something that's in the model right now. And we're making that assumption. And that does kind of align with what the average that we're looking at the moment. Looking forward, we wanted to make some model improvements. DTM mentioned this, that we're moving to an upgraded version of Plexos. That comes with a lot of verification to make sure that the data we have in an older version is still working properly. None of the new wonderful benefits of and attributes of the new upgraded model don't break anything that we have. So we're making sure that's there. We have all the required functionality that exists and consistency in what we're seeing. We are planning to make use of the expanded modeling options in the battery class in Plexos. There are quite a few more options for modeling in this version of Plexos. We want to make sure we're using that right. And we are looking at modeling individual specific outage characteristics like we do for power plants in general. We are still looking towards doing a 4-hour assumption for energy storage capacity for resources for the time being. Sorry, forgive me. If you have a question, please make sure I catch it. I'm not looking for standing up tags at the moment. For hydro modeling, this was another item that we discussed at our October 8 workshop. We took back the feedback that we had and we ran a high case and a low case for hydro. So this was with the all RA eligible scenario for scenario 3. And so from that scenario, that's the average hydro year of 2018. We ended up with 12 loss of load events. It was well overbuilt. This is where we got that 1,800 megawatt surplus from. When we ran it with the high hydro year, the number of loss of load events went down to 7. So that wasn't a drastic change, but those are the events that are harder to capture. And then when we went to a low year of a proxy year of 2015, we saw a significant increase in loss of load events. It went up to 73, which translated into a 0.14 LOLE above our 0.1. So this is enough for us to say, we do think this is important. We want to update our hydro model to capture some of that variation, and we want to make sure we're doing that right. So some of the things we're looking at for that is to move to modeling a number of historic years. Right now, we're looking at 25 years of historic hydro. Randomly pair those with the 500 cases that we have right now as another stochastic variable. And then, double check that, we're not getting overly drawn on any particular hydro year and understand how that's impacting things. Some questions that we have that we'd appreciate some input on and thoughts is really how many historic years should we use? Do we need to weight different hydrological years differently? If we're using 25 years, should they all be weighted equally? If we're using 5, do we need to weight a dry year more heavily than a wet year because we're using a smaller subset? And then do we need to look at aligning wind, solar, hydro, and load generation outputs from the same historic year and weather information? This kind of touches on some of that correlation that we talked about as well, but trying to understand what's the best way to insert these hydro profiles into the model.
Sorry to ask this question if it's been addressed elsewhere, but I'm just curious what it means when you pull 25, the distinct historical hydro years. Is that an 8760 dispatch, or are you giving it parameters where it has certain flexibility? Can you just describe kind of what that means with the historical data?
Yeah, Mike, if you want to jump in, you're much more familiar with the hydro at the moment.
Yeah, to answer your question is that when we're modeling the hydro, we separate 2 groups. One is Long River, another is dispatchable. So based on Long River, we just use the profile, but dispatchable we based on the RAM and also I think that also serve service. So they have different purpose for dispatchable. So in terms of when we select, I think the 25 years of the historical year that we may vary, I think, based on available data. We have from 2003 to 2024 right now. So we can capture majority of the hydro. And the thought that we like to have is, for instance, that we have the historical annual peak at 2006 and 2017 and 2020 and 2022. So if the hydro you select at different year, like 2015 is the drought year, and combined with those peak together, maybe we are going to add, I think, unlikely happening case into our study. So the thought that probably come from the same historical year that when we pick up, so wind, solar, hydro, and load probably come from the same historical year. Then it generates some kind of a correlation between those, I think, the wind, solar, and load together, and not give us a surprise, I think, that C to generate an unlikely happening case. So just mess up our thing that 500 is to X, so forth.
Yeah, I think that's valuable to have that connection. I guess my question specifically is about the available capacity by hydrological conditions. So in a drought year, I realize the energy is going to be a lot lower in drought years, but is your capacity also much lower in the drought years? Like, it just looks like a very large difference because the LOLE between the low and the medium and the high is pretty significant. When we've looked at this for CPUC in the past, typically the capacity is only a few 100 megawatts difference between those drought years. It's just the amount of energy is less, and so you have less flexibility with that fleet. Just curious if you see the same.
Yeah, I think that we deplex or we dispatch based on daily energy. And also I think that daily maximum and daily minimum based on historical data. And based on that to dispatch, of course, that capacity also have the impact. But majority of the case, the major impacts come from the energy. So for instance, 2015, that the capacity we still have, I think in the summertime, we still have some capacity reserve.
That's a dry year,
Yeah.
extremely dry, right?
Yeah, extremely dry year. Like I talked to PG before, I think that when we preserve, I think all those hydro, they usually preserve the water for the, I think that the severe year. Thank you. But they, for energy purposes, they could not consecutively keep those capacity for the whole week, whole month, especially in July or August or September. So they just for a few days. So they could survive, I think, that during the peak time, but they could not survive for the whole month. So in this way, when we do the study, then usually we base on historical daily maximum, daily minimum, and also daily energy and do dispatch. So in this way that we can observe that 2015 we have 73, I think that those LOE case, but in the average year 2018, I think only 12, and maybe just 2017 was, I think, only 7 cases.
So does that mean that you take the 365 daily maximums and put those into the?
Yeah.
So
based on historical daily maximum and minimum, and also the energy as a constraint when we simulate, I think, the whole package there. So in this way that we capture some of historical pattern, but not limit to historical, I think, every hour, because that they are consecutive, maybe 1 month, they do not have so much energy to support. In this way, we will catch a lot of the reserve energy there.
Yeah, I think the only challenge that I might offer to that is that there's more flexibility than what shows up in the historical daily record. So on a drought year, yes, we probably schedule less, but if I match that up to the conditions for that day, maybe it was a lower load day. Whereas in reality, so we look at historical events, even in a really dry month, we had a really extreme day. We're able to get 4,500 megawatts of dispatch on that day. But 3 days later, cold front came through. Nothing had changed hydrological from that perspective, but we just reduced the dispatch because now system conditions weren't as tight. And so recognizing, at least when we put in the inputs for a drought year, we'll put it in by month. So recognizing I have some additional flexibility beyond what the daily min, max, and energy was in this month. And maybe this is kind of to the point you're making that I couldn't do this for a long time for the whole month, but I've got a couple of days where I could change my dispatch beyond what the historical record showed.
Yeah, I think that in the past we have been setting as the monthly limit and also the monthly maximum and minimum to dispatch. So probably that can, I think, answer some of your question because your server model is based on, I think, weekly. So after that we found that I think we like to have this speed up, I think, that to reduce the computation of the whole model. It has been running for 1 week before we got an answer. But when we, I think, that want to reduce the computation time, so we reduce from monthly, I think, the constraint to daily constraint. So in this way, we reduce significant of the computation time sort into 1 date. Used to be 1 week to running for the 500 case and got the result. Right now, we got 1 day, then we got the result. That's why that we reduce some of the constraint and from MT to ST. So in this way, that the whole model right now very efficiently to running. So that's some of the, I think, that improvement made from that. But also some sort of that you mentioned about maybe 1 month, 1 week there, and considering more flexible to dispatch. So some of the, I think, the pros and cons that we come out with the result there. So so that was, I think, thanks for your, I think, that somewhat input there.
Yeah, I'll follow up offline, but there are probably other ways to implement that flexibility that wouldn't require that increased computational time.
Yeah.
We talked about.
Yeah.
Great. Yeah, we
Next,
appreciate
we have a hand raised online by Alva.
Oh, this is Elvis Svoboda at PG&E. Just relevant perhaps to the discussion that just happened. it would seem that, I want to double check because internally I'm told that pump storage is treated as hydro, and certainly pump storage would be available day in, day out during stressed conditions. So I'm wondering about the modeling of pump storage here. That might be on the next slide, but I just wanted to double check before you moved away from hydro as to whether it's appropriate to treat pump storage as hydro.
Do the pump storage we separate model, so it's not grouped into the dispatchable hydro. So pump storage can dispatch anytime that based on
Okay.
their needs. That
Okay, great. Thank you. That answers my question. Thanks.
Thank you. And I think Noah, you had a question.
On your slide 17, I guess, what's the sensitivity between the low and high year, like rough megawatt difference?
I don't know that offhand, Mike. Do you know? You put the low together, I believe.
That was significant difference, I think, that I did not have a very good memory of the exact number, but the 2015, it is the draw year based on the past 100 years. So you can look at the snowpack. I think that in the CDWR is showing that 2015 is the lowest hydro year ever. And 2017 pretty much close to 2018. And 2017 it is the second highest hydro year.
And so I think with this, we know we have quite a bit to look into for the hydro to make sure we're characterizing it right and modeling it as we move towards this. We just wanted to loop back that, yes, we do think that this is worth looking into. Zach, did you have a question?
I just had one. This is Zach Ming from E3 on the next slide. One pretty minor comment. I would recommend not correlating hydro with wind and solar and load. I think those conditions are sufficiently dissociated from one another that what you gain by correlating them is less than what you lose by being able to mix and match different conditions.
Okay. I appreciate the feedback. Okay. Yes, Doug.
Yeah, playing a little bit of catch up, so I apologize if this is already well addressed. In looking at the so Doug Karp of Peninsula Clean Energy, sorry about that, for those of you on the phone. Are you taking a look at changes in the distribution of hydro years based on climate change? I mean, we're going to expect potentially even drier years than we've ever seen in the historical record.
We aren't currently.
Okay.
I think we're open to that, but we don't have the expertise to pull that in at the moment in-house. So we need to figure out what that looks like, especially as I believe the CEC is moving towards incorporating climate change and distributions into load forecast. And I think they have some work that they're doing with that. And I believe the CPUC is also trying to make some progress there. So.
Okay. Yeah, I think CalCCA may have done some as well. So I'll circle back and see if we have sources for you.
Thank you.
So I have a question. This is Shiping Lee from CalISO. I think our hydro discussion here today originally from the concern about the low hydro condition could be make our system less reliable if we use the average assumption. So I'm just wondering, when we include this hydro year data, should we only include the average year and the low year, or should we also include the high hydro year? What's your response on this?
Yes, Kevin from Astrape, my perspective on this is if I know that it's not going to affect reliability, I don't have to necessarily do the simulation, but I should take that into account in my probabilistic assessment. So that represents 25% of the conditions that contribute 0 to LOLE. I could redo the calculations without running that simulation. But makes it more challenging. We just simulate it all. Typically, it's kind of our approach. So the full range of hydro conditions and factored in accordingly.
Thank you. Yes, Stephen.
Yeah, this is Steve Keen, Edison. I want to go back to storage for a minute and just, can you explain in the model how storage is optimized? Is it, I mean, like I guess I have a couple questions. One would be, is it limited to 1 cycle per day? The other one, is it optimized over the 24 hours of the day, or is it, because one of the issues that's come up and there's a whole thing going on in terms of how do you determine, it's the BCR for storage and how is their output determined? Because sometimes it adjusts on the day ahead, and I'm just wondering if that, how the storage is optimized to see whether like those issues are coming up at all in the runs or not.
So it's currently optimized. So we're running Plexos. We're solving the whole day at once with a 24-hour look ahead. So it's almost actually optimizing across 48 hours, but we're not using the second set of 24 hours. We're just saving the results from the first 24 and then moving on and doing the same thing and iterating. So the storage does have a lot of insight into how things can dispatch or what needs will be looking forward to the future and across that whole day. So it's optimizing across the whole day. And so that's probably going to be a little bit different than what happens in reality. But also it's useful for the model to understand that we need to keep energy around for later in the day. As to cycle limits, Mike, I don't think there are cycle limits in the model on a daily basis. I just wanted to confirm that. So that is impacting things, and I think you'll see a little bit of the difference between Plexos and Servum. Correct if I'm wrong, Kevin, but Plexos is Servum is dispatching the batteries a little bit differently. You do see some of that come up in the results. Does that answer your question, Stephen? Yeah. Okay. I'm going to keep going.
We do also have an online hand raised by Carrie.
Hi, this is Carrie Bentley with the Western Power Trading Forum. I was hoping to dig into that storage point just a little bit more in terms of practical impact on results, because we have, we're going to have 15,000 megawatts of storage by the end of the year, soon to have 20,000 megawatts. It really is supporting our hopeful achievement of the 0.1 loss of load expectation. And we do see pretty significant I would say suboptimal dispatch of storage in the real time. And so if we're trying to mimic real world conditions, it seems like, and I don't know if this is possible, so I'm hoping you could speak to it, there would be a way to have that reflected both in Plexos and Servum. And then the second point would be the same thing for the cycle limits. 90% of our battery fleet, maybe even 95%, is limited to 1 cycle per day from a practical warranty contractual perspective. And we see that, in the master resource database. And I'm wondering if we could reflect that in both models as well.
I think that's something that for at least Plexos, as we migrate to the newer version of Plexos and we have a lot more options with modeling batteries, those are things that we will look at and trying to optimize that. Optimize is the wrong word here. Try to improve how we're characterizing the energy storage so we capture some of the reality of what's going on in the system and some of those limitations, including cycling limits. Kevin, did you have anything to add?
Yeah, Carrie, and I'll speak to this more when I present on our results. Certainly lots of flexibility in Servum to reflect uncertainty. So you can create the schedules with imperfect foresight of load, wind, solar conditions, generator performance, import availability. So that will detract from the value of storage, and you can try to sync that up or calibrate that with market conditions. But again, I'll speak more to that when I present.
Okay, yeah, that sounds great. Yeah, I'm less familiar with Plexos. And so it's just interesting to hear the potential kind of unlocking of suboptimal conditions you could do with the next version. Thank you.
I'll just add also on we did receive some comments on the October 8th workshop with specific suggestions for storage modeling changes and how the storage is dispatched. So any detailed suggestions about kind of how to capture real world or sort of real market conditions in the model would be appreciated.
Yes, Mike.
Yeah, to answer your question is that I think right now we model the storage, battery storage based on pump storage classic module. So if we migrate to, I think that to 10.R7 then or 11, I think the Paxo with the battery module, then we can do a lot of, I think that feature like the ramping up, ramping down, also I think different sub dispatch. All those I think we'll implement in the future, I think in our new model there. So I think that we can do that. I think that a lot.
Absolutely. Thank you. Yes, Aditya.
I'm channeling my inner Shu Cheng here. I think the model will always be a little different than what happens in real time because there are a lot of folks manually working the system with conditions that are known. That's why we try to do a range of stochastic modeling behavior where we allow the model to have perfect foresight. While in real time, we operate with market rules and the operators have access to making changes in real time with exceptional dispatch and other tools that the model would not have visibility into. But
Yeah, I do think it's important to make the distinction though between variability in profiles and the uncertainty when decisions are made. And so we try to keep those distinctions clear when we do our servum setup that yes, we want to capture that variability. So we put in the 500 stochastic profiles. But if the model still has perfect foresight on those 500, so looking day ahead, I know exactly, hey, this is a really high load day. I'm going to optimize in a certain way. That's different than going into the day and there's forecast error on the load, wind, and solar. And how would an operator make a decision with that uncertainty versus how does the model with perfect foresight make that decision? And how does that show up in the value provided by the battery resource? It's possible to distinguish those in the modeling, do exercises both ways and see the impact. Just observation.
Absolutely. Thank you.
Yeah, I was just going to say, this is exactly what's been coming up in the storage BCR case where, day ahead, they're optimizing the storage because they're looking over the 24-hour period and they can set it up. But then when they get to real time, RA resources still have to put bids in real time. So the question is, what do they put in? And there's a weird situation where because of the way BCR works right now, if they're scheduled, to run at, let's say 7 o'clock at night, and they're going to make $100. Well, if they get that energy used up earlier because they're putting bids in earlier and they can't run at that point, they get BCR, so they get recovery for it. So it's unclear, there's essentially an incentive right now for them to bid to use that up, and that would create a reliability issue in that evening period. And that's, I think what's emblematic, the problem that comes out there is, when they're in the day ahead market doesn't look ahead more than a couple hours, so they can't see that they're going to need it, at noon, they can't see that resource will be needed at 7 o'clock. And I think that's exactly what you're talking about, trying to build in some of that uncertainty. And I don't have a good idea of how to handle it or what the implications would be, but I think talking about that is at least useful.
Do we have any other questions online we have another one in the building. Sorry.
Hi, Michaela Fly, Customized Energy Solutions. I guess with the uncertainty piece, to me, it would affect more than just storage assets. You do have longer lead resources. Do we just assume they're online and committed in the model? Because if there was high uncertainty earlier in the day, you might not commit that 4-hour resource. Mm-hmm. It just seems like it is beyond storage. Maybe the impact is less, but I'm just wondering if the incorporation of uncertainty in this model applies to all resource classes.
Yeah, sorry to monopolize the conversation here, Kevin from Astrapa again. Certainly, it makes sense to incorporate this for all resource classes. I do think the operating reserve inputs into the model are intended to mitigate that for a non-energy limited resource. So we commit enough so that we have enough resources on for those critical periods. If you look at the most extreme days, a reliability risk day, it's likely that even with any potential range of forecast error, those non-energy limited, so resources with firm fuel supply, dispatchable resources are going to be committed for that day. And if not, it probably prompts operating reserve review to make sure that practices for emergency days is kind of matching up with having those resources on. Now, if you look at like spring maintenance days where spring maintenance days that could be influenced by a couple of big outages that happen on a spring day and we didn't have enough committed, those are typically kind of when we see the forecast error influencing the value from a long lead time resource. But again, that's less of an RA question because we have enough resources. We just, operating practices need to be reviewed to make sure that we're committing enough to absorb the range of potential impacts that can happen.
Thank you, Kevin.
We also have a hand raised online by Kathleen.
Go ahead, Kathleen.
Thank you. Kathleen Colbert from Vistra. I wanted to return to the cycling limitation conversation and make an ask of the CAISO. So that was an interesting back and forth. There's a couple things that I wanted to note. The first one is that, you know, I've reached out to a different part of the CAISO team, right, the master file and the validation side, in the past to ask them about cycle limitations and whether or not there was a way to communicate that to the CAISO and have it be validated. And the answer that we've received is no, right? There's no master file field for this, and so they don't support that process. While in the back of my mind, that has been like a very low level issue, is that CAISO doesn't have a way to communicate that to them, nor like a validation process for it in the master file realm. I have to be honest, the list of issues that we need to address for storage is quite long. And given that I have deprioritized this one to basically not be one that I was planning to bring into the scoping for this upcoming effort. The conversation about how this modeling may or may not include cycling limitation assumptions hits me because it might be a valid reason to actually prioritize it higher. What I would need to know, and what the CAISO energy and market side needs to know as we think through the prioritization of our scoping is coming up in the new effort for storage, I think is really how sensitive are these results to you using a generalized assumption versus having actual data that you could pull from master file to inform, let's say, a more accurate assumption across your storage modeling. Does that make sense? Is there a way to assess whether or not the results are highly sensitive to getting the actual data?
Yes, we can assess it, but we have to just run with and without the data and assess how much that changes, and probably look at some minor verification or modifications to the system to understand.
That would be very helpful.
But it's something that can be done over time.
That would be great. I believe we're scoping in Q1 of 2025, so we have a little bit of time. But if you could take that ask and circle up with Sergio, that would be deeply appreciated. There's a lot of overlap between RA and the storage issues, and I appreciate your guys' efforts trying to help connect the dots, but this is one that definitely hits me as maybe you need a master file change to help you, but knowing how sensitive your results are to it will help indicate for the CAISO whether it's worth the lift. Thank you.
Thank you. Any other questions in the room or online? I'm going to move us forward. So one of the discussions that we had on October 8th was talking about the stochastic variables and the weather correlation that we have. So our stochastic process that's perturbing load, wind, and solar around a base case or a base profile is pretty good at maintaining the weather correlation or the correlations that exist in that base profile. So if you take a look at the solid lines across are the correlations of the base profile. That's not 500 data points. It's one data point just spread across the whole line so you can see the comparison. And so that base load profile without behind the meter solar and then the base solar profile, it has a pretty good correlation at 0.6 out of 1. So they're positively correlated. As load goes up, solar is typically going up. And that sticks around through this 500 samples as we move through it. Load and wind, however, are really not correlated, or essentially not correlated at all, and that remains as well through the 500 samples. However, solar and wind are negatively correlated. It's a light negative correlation, but that's essentially saying that wind is likely to go up when solar goes down, or a little bit more likely than to go up and down together. So these do remain, those correlations do remain through your stochastic process. There was some conversation about other correlations that may happen or changes across weather years, and we are hoping to coordinate with the CEC as they develop their stochastic load profiles and other profiles as well through some of those processes and continue to incorporate that and iterate and improve. Yeah. I can go to the next. Forced outages was another point of conversation at the October 8th. This is a quick comparison of just the forced outage rates that we presented last month to the CPUC's outage rates in their 2023 IPER, as well as GAD's data from their public brochure that was aggregated up by them. We are lower and we expected that. And so we do want to just iterate that we are looking at improvements here and go in a little bit more detail on what we're looking at and what data we have. But these aren't like we're orders of magnitudes off across the board, but it is something that needs some improvement. Looking at some data that we have from the outage management system, these are reported or logged outages for September 2024. We broke them out into what was reported. It does include both planned and forced outages as reported, and these are just specific events by resource type. So we can use this information along with the information I'll have on the next couple of slides to calculate outage rates that do and do not include different things like ambient temperature derates. And we want to make sure we're classifying these as this is a plant outage that we need to consider in forced outage, or is this something that we need to consider elsewhere in our model? So I'm going to highlight, just because it's a really shocking one, when you look at it, if you look at nuclear, it's planned outage. It's not a forced outage, but it's a planned outage. It's got 3 logged events, but if you look now at the duration in days, those 3 events covered 14.4 days in September. That's a significant amount. And if you look at today's outlook, it doesn't look like Diablo Canyon was out at all. So it's kind of an interesting thing to see here. So you can see that some of these, the durations that we have, some of them are longer, some of them are shorter. If you're comparing, some of them last on average a few days, some of them less than a day. But we do have this information to pull. Now, looking at this next slide, which is the total energy generation potential that's reduced by the logged outages. The units on this would be megawatt hour, but please don't confuse that with being energy that was not generated that would have been generated. This is just a reduction in how much generation could have been produced across the month by those outages. And if you looked at that planned maintenance or plant maintenance that's planned for Diablo or for the nuclear, it's at 64,000 megawatt hours, which translates into about 150 to 200 megawatts of outage each hour that it was out, given the duration. So we do have that information on the magnitude of these events, where they're occurring, how long they're occurring, and how often those things are getting triggered. So we want to start making use of some of this data, or looking at the possibility of using some of this data. And I will note that this is just for shown RA resources, the data that you see here, but we do have this data going back in time and for more months. One of the things that we're looking at now, and I'll make sure I'm on the right slide, is where to classify some of these outage types. Because not all of these are appropriate to call necessarily a forced outage. Some of them make more sense to attach to specific conditions or call them plant characteristics. So this is a very draft. Here's some options that we looked at. And this includes all the codes that are currently in the business practice manual for outage management. The link there does take you to version 30 of this, and there are some definitions in that as well. So we've tentatively lumped this into, okay, these outage types should be included in forced outages. Obviously, if it's flagged as a planned outage, we wouldn't treat it as a forced outage. For a forced outage calculation, that would go into another aspect. But then situational derates. Sorry, do we have someone online? No. Oh, okay. We have some situational derates such as ambient due to temp. Rolling that into a probabilistic forced outage rate doesn't make a lot of sense because that's going to be more tied to when temperature conditions are driving an ambient derate. We don't want to have ambient derates come up when temperatures are in the 60s. And then plant characteristics, including use limitations and environmental restrictions that are probably going to be more plant specific and won't show up in a random way. Or can't be accurately represented as a random outage. And then a number of outage codes that may not be appropriate to include, including such things like transmission-induced outages. That's important for us to understand, but to attribute those to a specific plant might be a challenge and might not be the right way to characterize it, especially if we're doing a class average. Some plants are going to be more likely to run into transmission-induced outages than others, or it could be a group of plants that hit that. Kevin?
Hey, Mark, Kevin from Strape. Curious how you impose the plant characteristics. Do you put in a discrete hours per year, dispatches per year for the conventional fleet that has these types of restrictions? And is that encompassing the environmental restrictions, or is that a separate, and is that modeled? Can you speak to that?
It's not currently modeled. So this is stuff that we're considering and want to look at. We, frankly, putting on specific limits might put some serious damper on our computational time, but it is something to consider as well. So I can't say this is how we've modeled it, but it is something that could be done in Plexus to say, here's your maximum output in these timeframes. Have that by month, or if it's continuous across the year, you can't hit more than 40% by the end of February for a use limited resource.
Gotcha. I just noted on the prior slide, it's like 1.5 million megawatt hours in the environmental restrictions category. So it looks like a pretty significant impact.
Yes, that is significant. So that's something we'd need to look into and make sure we're characterizing it well before trying to drop that into an outage in the model.
Yeah, thanks.
So we are interested in thoughts on this, where you guys think some things should fall or should not fall, and other ways to looking at this as we start to aggregate data and take a look at what we've got. The next topic we want to raise is to talk a little bit about what our loss of load event means. And just reconfirm, this is what we've been modeling with our loss of load model as well, and some of the differences between real-time operations and our model. So first, for the equation on the side, we just want to iterate that our loss of load expectation is the number of loss of load events divided by the number of sampled years. For us, a loss of load event is any day in which the total generation is less than load plus reserves plus firm exports. Since we're not modeling firm exports, that's essentially a zero for the model that we've got here, but it has to meet those loads and reserves. And we're only looking at RA resources. So for scenarios 1 and 2 last time, it was the resources we assumed to be shown. For scenario 3, which we focused on, that was all RA eligible resources. So it's a very small subset of what's available to the real-time system. Day ahead market and the operators, they have a lot of tools that we aren't attempting to capture. But we do want to understand, okay, at what point and how often are we needing to trigger those extra tools? And looking at bid-in resources and market resources as well. And so as it moves out from that center is really all we've got in this circle is in our model, with a little bit bleeding over into that second bubble because it's a little bit more than shown in our area resources. As that goes out, we do have access to energy-only resources, imports in the real-time market in the day ahead. And then it goes into Flex Alert as well, and all the reliability programs and supporting programs, RDRR, CIREP, EPA, ELRP, all of these can provide some additional capacity that is available to the market as well in the operators. And then to go to EEA 1 and 2, and then you don't start seeing actual firm load until you get to that EEA 3 where you're seeing some load shed, or you can see some load shed. So that's a big difference that we have between our model and system operations. So we don't want people to come away saying, hey, we're expecting to see, you know, a loss of load expectation of 0.5, say. That doesn't mean we're going to see that many loss of load events, in addition to just being probabilistic analysis instead of a prediction of what will happen. Some key things here is what's included in those reserves. So we brought this up and we talked about it last week or last month, but we want to emphasize this. We're modeling 7 different reserve types. Load following up and down are both presented in the same row here, but it is a separate reserve type in our model. So we are counting the reserves that must be carried for our loss of load event, or we trigger a loss of load event of regulation up, frequency response, and spinning reserves. And these are the amounts that we're required to carry. We do also have supplemental reserves in the model. It's not required to be carried before triggering a loss of load event. Neither is regulation down reserves or load following, but they are there. There's a penalty cost associated with them as well in the model to encourage the model to provide those. Some of these are reserves that don't necessarily exist in operations, but we're using to help mimic what's going on in operations. To help, I'm going to take a step back. We're modeling on an hourly basis. Operations cares about every instance. And so you lose something with that. You lose some of the ramping up and down within the hour. So load following helps us with some of that of looking at what's the intra-hour difference in load on an hourly basis and a 5-minute basis. Frequency response reserves is another reserve that we're including here. That's really mimicking the replacement reserve capacity for frequency response that's happening a lot, or that could happen a lot within operations. So we just wanted to highlight some of the differences that we have with what's going on in operations and what's in the model and why we're seeing some of those differences.
We have a couple questions online, if now's a good time.
Absolutely.
So first one came in written from Paul Nelson asking, is the DWR strategic reserves included or excluded when an outage occurs?
We're not including the strategic reserve in our model. So that would be something that our loss of load event wouldn't have accounted for. I'm going to say that a different way. We're not modeling the OTC plants. They're just not in the model at all, except for Diablo Canyon.
All right, and next we have a written comment from Peter Greifs asking, is it proper to call it a loss of load when there's so much capacity available that is not modeled? Isn't it more accurate to call it avoidance of strategic reserve expectation?
Possibly. I think loss of load expectation is what people are more familiar with for what's in our model. I don't know, D2, do you have any thoughts on that?
Yeah, it's a little different when we say expected unserved energy in our model. It basically is going into emergency operations, not necessarily firm loss of load. I think that's the distinction that we've always kept historically. If that needs to be changed, we can look at it. But the strategic reserves, at least the large OTC plans, are only here for until 26. They're slated to retire at the end of December 2026. So I don't know if you want to make that change, we can. But the philosophy is, what is the probability of us getting into emergency system operations is what this is trying to assess.
Yeah, I'll just offer some perspective from other markets. This is a pretty consistent thing that we find is that you will still model some reserves during load shed. I think in practice in 2020, ISO actually maintained over 5% reserves. So they shed load in order to maintain, to preserve some reserves. Whether you would still maintain that in a future event is to be determined, but there's the assumption to maintain system stability, you need some reserves still. Almost all of our clients still preserve, it's usually in the range of 2 to 3% of total load that would be preserved for load shed, where this translates more to 5 or 6% in aggregate. So that may be on the high side, but still the perspective is in your planning exercises, do we want to plan to maintain the level of reserves that we've identified as appropriate for operating the system versus do we want to recognize maybe in the short term, we've got some flexibility to deplete some of those reserves slightly. So I think it's prudent in your planning exercises to put what your system operators have actually implemented as this is a prudent level of reserves to maintain. So, and still calling it loss of load expectation that we're planning to maintain 1 in 10 while still preserving our total aggregate reserves.
Yeah, if you go to the next slide, I think we say that we're only preserving the spinning reserves portion, that's 3%. And the supplemental is not included in the, it's about 3.5% maybe, or whatever. That 376 is a small amount.
If I include the regulating reserves in that, I'm getting closer to 5 or 6%. I was adding up 1, 2, and 3 to.
Okay. Is it for some hours? Is it that much, the regulation of reserves? I thought the max I saw was 1,400.
1,400 as a percentage of load would still be 3%.
Yeah.
Yeah.
So we're up there pretty high for compared to the organizations you were mentioning.
Yeah, I just want to add in our summer assessment, we didn't include the strategic reserve as a part of our planning practice because those are meant to, resources reserved by the state for like an actual safety cushion in addition to what we normally have.
And I think, thank you, Shuping. I think that highlights some of the difference in that analysis and its purpose compared to here, where we're trying to look at setting a default PRM and qualifying capacity rules, is we don't want to include resources that are outside of that, but we do still do assessments where we include those resources as well.
We also have a few hands raised online.
Great.
First up, we have Carrie.
Hi, this is Carrie Bentley from the Western Power Trading Forum. Sorry to push you back a few slides, but can you go to slide 23, the one where you had the outage data? So in this data, is this inclusive of the SRR resources? Because the environmental restrictions, other gas, I'm assuming that's the strategic reserve, and that's why that's so high.
Yeah, that's what I was thinking too, Carrie. I did the math. If you go to the previous slide, it's only 9 megawatts off in environmental restriction. That's the shown capacity. So that might
this is only 9 instances.
9 instances. But the next one was
yeah.
megawatts, right? So megawatts was 161 megawatts.
No, so sorry, this is the days that it was impacted, and then this would be total megawatts by hour. So some of these outages are logged for less than an hour. Some of them are for more. And so we aggregated together by putting a time component to it. So we'd have to double check to see if the OTCs are included in this. I don't know offhand. Sam, you pulled the data. Are the OTCs in there?
Yeah, they are.
They are. Okay.
Okay, that data makes a lot more sense then, since they're, basically permanently on environmental outage and only came off for, a handful of days in September. Then the other question I had on this was I was looking at the battery plant trouble for forest, and that was an incredibly high number to me. And I'm wondering, is that both charging and discharging energy?
Sam, do you recall the batteries?
Sorry, I missed the question. Can you repeat it again?
Was the plant trouble for batteries, does that include both charging and discharge limitations?
I don't know that off the top of my head.
We'll have to look back at it and make sure we're pulling this right.
Okay, that would be helpful. Just as a kind of an aside to this, if that's just discharging energy, that, I mean, it's not this initiative, but would make me think, oh my God, what's going on with our storage fleet? That's an enormous amount of outage energy for storage, right? I mean, it's almost comparable to our combined cycle fleet, which is 3 times the capacity, and it's summer, so we expect the ambient D rates. So just would be helpful to have a follow-up on this chart. So I know whether this is an action item we need to take outside this. And then, oh, go ahead, sorry.
No, I was just saying thank you. Please go ahead.
Yeah, and then just final comment, I think we should stick with the name loss of load expectation study. California has such a terrible habit of renaming things that the rest of the country then can no longer understand. I think everyone knows what we mean by an LOLE analysis, so I hope we don't rename it. That's all. Thanks.
Thank you.
Next up, we have Kyle Navis.
Hey everyone, thanks. Kyle Navis with Cal Advocates. Mark's point that this is intended to drive towards setting a default PRM, I think that's useful insofar as we're thinking about testing reliability for next year. I just want to, reiterate that the strategic reliability reserve is of the OTCs and the handful of peakers is something to the tune of 2.5 gigawatts. And so I think what would be helpful is to see the distribution of the magnitude of the loss of load events when the year ahead study is done, to understand how many loss of load events surpass whatever the expected contribution of the strategic reliability reserves would be afterwards. So there's no need to include them in the model, but to see, once you get the outputs of the model, how that fits up against the reliability reserve that we see come online, or that we see online in the specific year that we're analyzing.
Thank you for that input.
Next in the queue, we have Perry.
Hey, this is Perry Servideo, CISA. This is a good slide to just start on, but I do have a question related to slide, I think 25 or 26. But here, this is just a clarifying question. So is this just this data? Is this just the straight forced outage data pulled out of WebOMS and no other sort of filtering done to it?
There was some other filtering done to it. It was something that we had on hand to do, but it's not a complete report. This is mostly for example information, not this is data that we will use.
Okay, no, that's good to hear. I think that if you're going to use this data to start to derive, say, effective force outage rates and whatnot, you'll want, at least on the battery side, you'll want to tease out any outage that was related to managing the SOC, because your modeling will be modeling the SOC management. So it would make sense to reduce these quantities by the portion that was used to manage SOC. That's my comment on that. If you could go to slide 25, I believe it might be 26. Yeah, 25 and 26, I guess. I want to say this is a reasonable assumption, and this is the way also that that CAISO's market will behave in the way that the penalty prices are all set up. Is you will operators will shed load to maintain the level of reserves, and the reason they do that, I think Kevin was hitting on this, is because you could end up in a situation where if you're not maintaining reserve, you're shedding load to maintain control of the system, right? If you shed your reserves and in your load shed, then you're at a point where you're one contingency or one event away from a complete uncontrolled blackout. So I just wanted to support the concept here that you should be, the modeling should represent what you're going to do in real life, and in real life you will be maintaining those reserves at all costs. Thank you.
Thank you. Thank you.
Last hand in the queue is Doug.
Hi, Doug Bocignone from Flynn Resource Consultants for the Bay Area Municipal Transmission Group. I just wanted to comment on, looking backwards at how much load was shed. I think we need to be a little bit careful. my recollection is that we have had some instances where CAISO was supporting low priority exports, but still shed CAISO load and in real time. And, I'm not sure we should take that as, that's how the CAISO will always behave. I mean, the rules have changed over time. So, I think that might be why I think Kevin pointed to some historical outages. And, it wasn't just serving CAISO load in that scenario.
Thank you.
No further questions in the queue.
I'm not missing anyone in the room, right? We touched on like 3 different topics again. Okay. Last slide I have is a quick comparison of the NQC lists from 2024 to 2025. I believe these were both published on October 10th, so last month. And you can see that there's a fairly big difference in the total NQCs, primarily in the summer months. The bulk of that change goes to energy storage and solar. The energy storage change is largely attributable to new capacity that came online, whereas the change for solar was largely attributable to the changes in qualifying capacity accounting rules. For example, there's in July 2024, there was about 16,600 megawatts of solar, providing 2,300 megawatts of NQC for 2024. That now provides 9,300 megawatts of NQC for 2025. That's a big shift. It's something we just want to highlight and be aware of as we're doing this, and it's going to change how we look at that NQC list and how the NQC numbers translate to what's in our model. Christina, did we have someone on? No, okay. With that, that's the end of my presentation.
Cool.
I think we're going to go to break.
Yeah, we'll be taking about a 15-minute break. Thank you. Hi, everyone. We're going to get started again, discussing long-term and short-term results with Aditya.
All right, thank you, everyone. Hey, before I go into the midterm and long-term results, I wanted to take a second to talk about what Clyde mentioned about reserves. The standard that we currently are modeling is a VEX standard that requires us to carry 3%, but we will be, the VEC will be moving to carry the most severe single contingency going forward, which will bring down our reserve requirement. So that when that happens, we will model and reflect that new level of reserve need in future after it's filed with FERC and approved. All right, so going back to the philosophy of what we are trying to do, we're trying to assess the resource adequacy in all time frames, as we said, midterm and long term. So now we have to represent what the midterm portfolio would look like and long-term portfolio would look like. In an effort to do that, we've consulted with Strape to get a view from SERVEM model representing that with same set of assumptions, which Kevin will go through in a little bit. But I kind of wanted to quickly say that the short-term analysis, the year ahead work was done in Plexus using the 2023 IPER. Midterm and long-term, the years are defined as 2 to 4 for midterm, 5 through 10 for long-term. Midterm has existing all RA eligible resources and authorized procurement levels. So when you look at the MTR, 2,000 megawatts each for 25, 26, 27, 28, you have resources that meets the MTR amount is modeled. And when you go to 5 through 10, we modeled LSC resource plans that were collected as part of the preferred system portfolio exercise. There are It's not PSP exactly because PSP also has resolve additions, but this one is only modeling the LSE plans as is and still uses the IPO forecast. This is a graphical representation of how the NQC values change year over year, midterm, long-term plans. This is more representative of nameplate capacity additions that we've added to 26, 7, 8. These resources, and even going into the future for the LSE plans, it looks predominantly solar, storage, and wind resources. All of these additions were modeled, but we also included nuclear retirement. Diablo 29 and 30 were modeled in the long-term study. But everything else is resource additions, meaning no gas retirements, for example, no new resources that were part of resolve additions that you would see in PSP. Yes, sir.
Steve Keen, Edison, are the wind additions, are those in-state or out-of-state?
Both. I think 2030, you have 2,000 megawatts of out-of-state wind, right? Yeah. Awesome. I think now I will pass it. Oh, this is showing that demand and energy is increasing, as shown in the IPO forecast for the 10-year time frame. Now I'll pass it to Kevin to walk us through the analysis. Thanks.
Thanks, Aditya. And I'm going to apologize before I get started. The conversion to PDF threw off the font in all these, so it's terribly hard to read. Apologies for not coordinating better on that. This is not the actual font that we use on the subsequent slides. I'll introduce myself real quick. So I founded Astrape Consulting in 2005. We merged with PowerGem in April this year. So you're going to start to see the name Astrape go away a little bit sad. It's my baby. But merged with PowerGem, transmission adequacy firm, offer a more comprehensive set of solutions to the industry, both on the software and consulting side. So I'm going to talk through model setup. I made some notes here today. I think probably what's going to be most interesting to folks is some of the comparisons between models, between input assumptions, not just Servum versus Plexos, but Servum versus Servum, CAISO versus CPUC. I'll try to offer some observations, but obviously don't have a lot of the details here, and want to also recognize that I didn't do much of this work. Most of this work was done. We've got internal teams at Astrape that kind of manage the different engagements across the West. Joel Dyson did most of the work, and some of the other analysts that worked on this. So give credit to them. Unfortunately, I may not be able to answer some of the questions that come up, but I do kind of understand generally California modeling. I've been doing work for CPUC for over 10 years, so hopefully I can provide insight both into Servum and assumptions that we've set up for California in the past. So a little bit of background on Servum. You guys have probably seen the name of the software, various jurisdictions. Kind of going forward, we'll be doing interconnection-wide studies for both the West and for the Eastern Interconnect. Different parties will be doing that, but that will be done with Servum and for Texas as well. So all the regional entities licensed Servum will be using that for performing these energy adequacy assessments going forward. It's used already for a lot of the NERC probabilistic assessments. So kind of a lot of work in the strategic resource adequacy across the country. This doesn't show many of the, or any of the utilities that license Servum, but within each of the structured markets, obviously there are a lot of utilities that use and license Servum for doing their resource adequacy work. Servum is a bit different from most typical resource adequacy tools, which are generally accounting tools. They are stacking up resources and comparing the load. Servum is doing a full economic commitment and dispatch, which is one of the value that we see in CAISO running Plexos for looking at RA, that we're trying to replicate the way the system actually works in order to understand reliability. We think that that's critical for looking at RA. It's not just a function of stacking up resources and comparing the load. I won't spend much time on these slides, but just kind of a snapshot. For 2025, the first step that we did was to calibrate the results of Servum with results from Plexos. So we tried to replicate the same system that they have in Plexos, obviously recognizing their model differences, and I'll speak to some of those, but the same resources, the same loads, the same 500 stochastic renewable profiles. We attempted to model the same economic parameters on the physical resources, so non-dispatchable are excluded here, or energy limited resources, but the thermal dispatchable stack. And this influences how the resource commits and dispatches units, obviously. The geothermal biomass biogas was modeled as must run. We have a forced outage rate, as Aditya had discussed earlier. I can't speak to the precise numbers on that, unfortunately. I'm a little bit removed from that. The way that we model the ancillary services, similar to how it's set up in Plexos, we have hourly profiles for reg up, reg down, load following up, load following down. We did adjust those going forward through time to reflect that the reg up requirements will change as the solar penetration changes. We have this static 376 megawatts of frequency responsive reserve requirement in, and then a 3% of hourly load for spinning reserves. We also have, we mentioned load following and other reserves that are not protected during load shed. So we did replicate the same methodology that Plexos has with the specific reserves that are preserved during load shed, the reg up, frequency responsive, and the spinning reserves. Just a visual of the additional regulation required for solar as the penetration increased over time. So the total size of the reg up, I guess this is aggregated average across all hours in a year, but 40% higher regulation requirements out into the tails of the study years, study horizon, with 60 plus gigawatts of solar. All right, so we're trying to sync up some of the assumptions going forward, recognizing that behind the meter solar, there's some uncertainty in terms of how much and what those profiles look like. We took the 2025 ratings by zone provided by CAISO that were used to build their 500 profiles. Into the future years, we actually used the CPUC behind the meter solar installed capacity estimates for 26, 30, and 34, and still kept the same solar profiles we got from CAISO, but just scaled those up as the size of that behind the meter solar grew over time. In addition, for the future years, we incorporated the CEC's forecast of AAEE, AAFS, AATE. Ultimately, kind of in the long term, these have a pretty big impact. They're really significant programs, and they influence the reliability assessment. But for 2025 in the exercise, we did not have any of these incremental load modifiers. But going forward, we did include those. Yep.
Just going back to the previous one with the behind the meter solar, are you treating that as a demand modifier or as a supply side solar?
Yes, I mean, essentially in the model, they are all coming out of loads of a demand modifier. All non-dispatchable resources are subtracted from load before the simulation starts, essentially. So you have the variability that's incorporated from those resources that shows up in the net load profile, but it all happens on the front end. So they're treated the same as the utility scale solar in the model. I don't know if that answered the question or not, but all non-dispatchable resources and their attendant, if you're modeling V rates or partial outages on those, we do those calculations on the front end of the simulation. So we're committing and dispatching against the net load profiles that the model has.
Okay, thank you.
Yeah. Okay, so first exercise was to benchmark Servum and Plexos. Went through a number of iterations on this. Don't want to minimize the effort involved here. We did want to do a thorough job of benchmarking the results from Servum, the Plexos, to isolate what is due to an input difference versus what's driven by modeling framework difference. So I'll speak to some of those as I go through, but not a huge amount of detail on the input and the assumption differences. So we did replicate the 500 demand and renewable profiles. So we explicitly have the same solar, wind, load profiles for all 500 scenarios. We match the generator lists along with their constraints, so storage durations and forced outage rates. Key differences, though, within the modeling framework, we did implement a different hydro modeling concept. So instead of the daily constraints that Mike talked about earlier, we're modeling monthly constraints. So we have typical average daily dispatch patterns as a constraint and then max monthly constraint. So we might get more flexibility out of hydro on the most extreme day of the month rather than reflecting, hey, we have these specific limitations on each day based on the historical. Now, we did use our own hydro assumptions for this. I anticipate that they probably ended up showing less contribution to reliability than what the CAISO, but I don't have discrete data points on that to provide. But hydro modeling is a difference where we've got additional flexibility, but potentially lower inputs in terms of the flexibility that the hydro system has. Generator outages, we have random samples in each one of the scenarios. So we didn't fix a set of outage profiles for these runs. So on particular days, if we're comparing, that's going to be a big difference, is that our outage profile may be different than the CAISO outage profile in Plexos. So some days we may have more, some days we may have fewer. And then the storage dispatch, particularly during unserved energy, there was a question earlier on this, how is storage modeled? On a typical day, we will perform economic arbitrage. So the model will be used to serve ancillary services, but it will also be used to shave peaks and fill valleys on the net load in order to minimize production cost impact, minimize production costs. On unserved energy days, though, the model will use all available resources as needed. So if we get into a tight hour, even if the model had scheduled that in order to shave the peak, we're going to operate over this longer range window. If we are short and there are no available resources, we will dispatch as much storage as we need to keep the lights on. So with the optimization framework in Plexos, at least the particular configuration that CAISO is using right now, it's going to maintain that peak shaving, which means on an unserved energy day, you're going to have flat unserved energy across that entire window, whereas in Servum, you're going to delay or avoid that firm load shed until all the storage exhausts. And when the storage exhausts, you end up with a bigger load shed event. We think that this replicates operations, that in operations, if you have so many resources, you're going to use those until they're exhausted. And then when everything's exhausted, that's when your load shed occurs. So you'll see some of that difference in the profile comparison I'll show in a moment. All right, so just a couple of days that we pulled out of the model to compare against. So this is kind of unit category level dispatch patterns. I'm not going to talk about each one of these. It'll actually be a little bit clearer when I look at the difference between Servum and Plexos, but just confirming that resources are operating as expected, that we're getting import contribution prior to the net load peak. We're getting significantly more imports, and then during the peak hours, subject to the constraint that we have, 5,500 megawatt constraint, kind of in our base case. You can see the storage dispatch that's operating during the net load peak periods. We have the unserved energy during the net load peak periods as well. Similar dispatch profile to Plexos. In order to really isolate differences, we had to look at the differential. And so unit category level differential, and Mike and I were chatting about some of these differences before, that prior to the peak, we're actually importing significantly more energy from the marketplace. And this is just a single day. So this is not true for every day that we did this analysis or that we had unserved energy, but on particular days, we did see this pattern at times that we imported more in Servum than in Plexos. So it could be that we don't have the same hurdle rate, wheeling charge rate, which makes the imports look more attractive in Servum than they are in Plexos. So you can see in Plexos, they are dispatching more thermal. We are pulling in more from the marketplace in the hours prior to the peak. Our hydro dispatch, we're getting less hydro dispatch across most hours of the day. Demand response, we get slightly more demand response during the critical hours. But the big one is the storage dispatch. So the storage dispatch, Servum has higher storage output in hours 17, 18, 19, 20, and then significantly less storage output in 21 and 22. This is driven by the optimization approach versus use it as you need it. So in Servum, use it as you need it. 17, 18, 19, we're short. We're going to go ahead and use those storage resources. And that means that in Plexos, we actually had unserved energy in those hours. In Servum, we didn't have much unserved energy in those hours. And then in hours 21 and 22, we've exhausted the storage. We end up with unserved energy in Servum. We didn't have that in Plexos. So you can kind of see the light blue versus the dark blue line crisscrossing there. That's what's driving that, is the difference in approach for the storage. Any questions on that? Does that make sense? But ultimately, we got comfortable that we were replicating the inputs, that we could explain any differences in methodology. I'm not going to go through these individually, but we compared several peak days, cases where we had unserved energy in Servum, we didn't in Plexos, or vice versa. Yep.
Going back, you show the different, trying to figure out where the storage is charged. Is that in what's labeled as pump, what is it, load plus pumping? Is that where you're charging the storage? Or is that,
yes,
is that pumping referring to the pumped hydro, or is it?
That's all storage, yeah.
Okay.
Yeah, so either charging or pumping. So this is just Servum. This is not a comparison case, but just showing that outage draws for, this is just a single iteration for those particular samples. So sample 67, 148, 287 were really high net load variability cases. How did the conventional fleet perform? So we had a range of 2,000 megawatts offline to 5,000 megawatts offline in the conventional fleet. That resulted in the corresponding unserved energy profile that you see there. A question in the chat?
Not seeing any questions online.
Okay. Comparison of the outage profiles. So ultimately, these outage profiles are stochastic, so we get the random draws. We wouldn't expect necessarily alignment on any particular daily snapshot, but in aggregate, we should get the same average contribution, but just showing that some of the differences in unserved energy were driven by the particular samples. So in Servum, sample 67 versus Plexos, so significantly more generator outages in Servum than in Plexos. On another day, we had very similar, 287, similar outage profile. And then in 148, we had more outages in Plexos than we did in Servum, which is what we'd expect with the stochastic nature of those outages. Resulted in the surplus differences. So relative to that 5,500 megawatt import limit, Servum showed about 1,400 megawatts of surplus. So we dialed down that import constraint, or dialed up the import constraint, I guess, made it more binding by 1,400 megawatts to calibrate to the 0.1 level, versus that same exercise in Plexos showed 1,800 megawatts of surplus. So about a 400 megawatt delta between the two models. So the effects that I've talked about, or the modeling differences that I've talked about, the hydro approach, the forced outage sampling is driving part of that. We also have differences. When we ran this in Servum, we did this with 5 iterations for each one of those scenarios. So we did 500 times 5, recognizing that 500 iterations is not enough samples to get a conversion answer. So if I look at a single sample, this answer is, your confidence is plus or minus 150 megawatts. If you run it with 5 samples, 2,500 total, you get a little bit higher confidence level. So that can be affecting it. Also, the configuration in Plexos can affect whether you're using an LP or a MIP to optimize the resource utilization can affect that. So there are various differences that can influence it. We got comfortable that this was an acceptable level of difference based on the different modeling frameworks and so forth. Question?
Quick question. If I remember well, the first result we got from Kaizo in October, and the surplus from Plexos of 1,800. And what you were showing earlier, there was a big difference in the net import. So I'm very surprised that you have way more imports, and actually in the final result you have. So what could be the other?
Yep. So the difference in imports during the critical hours. So in hours that we had unserved energy, we had identical imports. The green line in hour 17 through 22, 16 through 22 are identical. So there's no difference in imports during the critical hours.
Thermal then? Okay.
So serve them in hours prior to the peak influences, which will keep energy limited resources maybe more fully charged. But you got the offsetting effect of the thermal fleet in the Plexos run. So I don't think it makes much difference in the result. So we're really concentrating on hour 16 to 22, same import level. We're actually getting a little bit more thermal from serve-them. And then you have that interaction or the difference in the storage dispatch influencing the EUE. Any other questions? All right. Go ahead and present the results of the mid long-term study. So just again, showing the same information that Aditya showed a minute ago. Obviously, the QC surplus calculation different than the actual reliability contribution, getting the precise contribution calibrated from serve-them. But it does at least illustrate kind of the trend that from 25 through 30, we have the increase in QC and then a declining QC after that. You'll see that same effect in the surplus calculations out of serve-them. So this is the calibrated results, 2, 1, and 10. So how much surplus did we have relative to the starting point of the 5,500 megawatt import assumption? If we remove 2,352 megawatts of that import capability, we end up at 2,352 for 2026. Did want to provide a point of comparison on that. So 25, we had roughly 1,400 megawatts of surplus. So we increased that surplus by roughly 1,000 megawatts to 26. That corresponds with the increase in QC and the increasing load as well. That balance contributes to 1,000 megawatts additional surplus. There is some challenge in calibrating to the load levels. So all the different models that are floating out there, the forecasts, got a consumption peak versus a managed peak. So in our setup for these runs, we used and apologies if I missed some of the details on this, but essentially we have a consumption forecast. So we used Kaizo's consumption forecast and tried to sync that up with the same approach that they used in 2025, which got them a managed peak that was very close to the CEC's managed forecast. We put in that same consumption forecast over time, so using the CEC consumption forecast, but we have these different profiles. So the solar profile can affect, the behind the meter solar profile can affect where you end up as far as managed peak. We ended up lower than the managed peak in 26 through 34. I think roughly 400 to 700 megawatts lower managed peak. So if I compare this to work that Donald and team have produced for 2026, I think they showed roughly a 1,500 megawatt surplus. A lot of that difference is probably driven by the difference in managed forecast. So we're within a few hundred megawatts of the managed forecast, but that probably explains why we're showing 2,300 megawatts of surplus and Donald showed 1,500 megawatts of surplus. And Badad may speak to that later, but we did get confidence that all in all, we're synced up pretty well. Obviously, we got big differences in the synthetic profiles that go in here based on the 500 profiles that and team produce versus the 23-year profiles that Donald and team produce. But in aggregate, it seems that those assumptions, the stochastic profiles, drive you to the same level of total surplus when you account for all the various factors.
Yeah, Doug Carpa, PCE. This is, sorry, this is on an ELCC basis or a nameplate?
It would effectively be on an ELCC basis because we're dialing that based on a perfect capacity addition on the imports. So the total surplus increases from 26 to 30, you end up with 6,000 plus megawatts of total surplus in 2030. And then as nuclear units retire, the additions don't keep up with the load growth relative to the 2030 value. That surplus gets eaten into.
Kevin, maybe one thing I'll add, the exercise, if we did try to bring the two models closer with terms of how we model LP and MP, we would be within 50, 60 megawatts, right? 1500 megawatts was our surplus in an LP run, which is 1437.73. So, right?
Yeah, for the LP run for 2025, that was 1605 megawatt.
Okay, 1600 and 1400. Once you bring the outages and the variability, it'll be pretty close. The idea was to do a quick benchmark. We could still optimize and refine to get those numbers closer, but that was not the effect. That was not the intent of the exercise of benchmarking. We wanted to make sure that the future year numbers make more sense, and that hinge was the benchmark exercise. So I think that's the key takeaway. Back to you, Kevin.
Other questions? I'll go through some of the heat maps from the results. And honestly, all these are calibrated. We pulled these results from the level that we simulated closest to 1 day in 10. So not precisely at 1 day in 10, but wanted to illustrate what those events look like at 1 in 10. How large were they? How long did they last? When did they happen in the day? So you can see the heat map there in 26. July, August, September, all the events are concentrated there. I did want to point out there's a disconnect between hours 18-19 versus 22-23. And we'll see this as a persistent artifact in all the simulation years that we look at. Now, we understand this effect. We see this in lots of modeling for CPUC and others, is that the reliability events in systems that have increasing energy storage penetration can be driven by one of two factors. One can just be a capacity shortfall. So we're adding storage resources that they have a capacity contribution. They also have an energy constraint. So in hours 18-19, that capacity shortfall can drive unserved energy. But if we fully use or exhaust those batteries, then in hours 22-23, we can have separate events. And this is generally driven, different days have different factors that drive those. So some days are capacity shortfalls, other days are energy shortfalls. There are some days where we have both a capacity shortfall and we still exhaust the batteries and end up with an energy shortfall as well. But that's really what's driving concentration of events in hours 18-19 and then separately in 21-22, and you'll see that persistently. The max shortfall, 6,500 megawatt hours, so 1 hour with 6,498 megawatts of capacity shortfall. And the longest event was a 3-hour event. You can see the scatter plot there, very few. Most of the events are concentrated 1 and 2, just a single data point there at 3 hours. And these are all going to be very similar. Happy to pause for any particular year that you want to dive into, but there aren't discernible trends that say as the storage penetration increases that we get a higher concentration of energy constrained days driving the event. We are essentially keeping the storage contribution balanced as we add lots of solar, kind of the need for duration remains relatively constant. We've seen this in other work with E3
We have a quick question.
Yeah.
Steve over here.
Steve Keen, Edison. Going from 26 to 27, I think the red one, which is I assume the most likelihood of outage, goes from July to September. It's in hour 22, but it's shifting from July to September.
Yeah.
What's happening between 26 and 27?
Yeah, so higher solar generally means you get less contribution late in the day. So we have seen a shift with higher solar penetration, a shift from July to September events. And those September events are going to be mostly concentrated in the really late evening. But if I scroll through other years, you can see in some cases we end up with concentration back in July. So it's delicate. I guess it's not perfectly balanced that we're going to move all of our events to September, but there is a slight trend that you're moving toward September events driven by that increasing solar penetration that it continues to contribute for July events, but it no longer contributes as much to September events. We do see, so the max shortfall in the range is 6 to 10,000 megawatts. Again, I'm hesitant to declare that as a very dogmatic trend that I would expect to see over time. By 2034, we did surface some long events, but again, you can see they make up such a small percentage of the overall distribution that, again, I wouldn't categorically say that that's a trend that we expect, that all the events will get necessarily longer. I do think that you see a longer window of critical hours, and Zach will talk about this later today, that we think about hours that really matter for reliability. It's not just the unserved energy hours, it's any hour in which you're discharging energy limited resources. That's it. Any other questions?
I like to add one point here is that when you look at the maximum shortfall, I think that the survey model showing that was at hour 22 majority of time. I think that from 2026 to 2034. And as we observe, I think that in 2025, that was because of the battery storage dispatch pattern difference, and Plaxo, I think, that's showing the maximum shortfall would at hour 19 or 20. So you can see that because of the software dispatch pattern difference, so which result in the maximum shortfall happen at different hour there. And the Plaxo showing the maximum shortfall usually happen at the next peak at hour 19 or 20 there. So you can see that discrepancy there. That was some of the, I think, the observation there.
Yeah, I think it's something we could explore more. We have configuration options in Servum to dispatch the same way that they do in Plexos. I think maybe vice versa. So we can certainly explore some of those differences in a little bit more detail. So it's not necessarily a ding on either one of the models. It's just a different setup that we had. I will recognize that in all these runs, so when we're doing these simulations, we're testing up to 10 different levels of import assumptions. We're running for 5 iterations for each one of the 500, or 25 iterations for each one of the samples. So instead of just 500, we're doing 500 times 25. So when we run the 500 samples, and that's the only case that we study, it takes us on our bank of machines about 10 minutes to run that full set. We're running 1,000 times as many as just that 500 sample. So quite a few simulations in order to get this full kind of 10-year cycle for all the different scenarios that we look at. I'm able to run through that pretty quickly. All right.
Doug has a question, Kevin.
Yeah, just briefly. Doug Karpa, Peninsula Clean Energy. So if I'm looking at this right, it sounds a little bit like from our conversations from yesterday that we need to be thinking about a lot more than just net peak at this point. It's really net peak after the batteries run out is when we really need to be keeping our eye on that ball as well, just sort of qualitatively.
That's right. I mean, I think from an accreditation standpoint, certainly you would expect that the biggest hourly driver would be those net peak hours. So while this, we think, kind of reflects how it would be operated, if I want to understand the value of energy, it is going to have the most value in that net load peak hour. And honestly, any hour that storage is dispatched, that eventually exhausts in the model. So the hours after the net peak from an operational standpoint, hopefully we never get to the situation where we exhaust all the batteries and have to shed load in hour 22, 23. Ultimately, the goal is to recognize any megawatt hour that contributes directly to reduced unserved energy should get credit for its contribution. Another question?
Yeah, Steve Keen, Edison again. You said one of the differences in the dispatches between the two was imports. I'm just wondering, one of the things we've been seeing, I think, is that, net imports dropped to zero during the, early afternoon period. Is that showing up in both of the modeling? Or, if you said if Servum is using more imports, are we not seeing that?
So the imports that I showed on here were the Delta imports. The Delta imports were zero, but we were still getting 5,500 megawatts of imports during hours 16 to 22.
Okay, I'm asking more about like 12 to 16. What was happening at that point?
So in hours 12 through 16, where we are getting, and Servum is getting more imports than Plexus.
Yeah.
Yeah, so Mike and I were talking about this, that it's probably an input difference that we didn't impose either a hurdle rate or a wheeling charge rate. And so the dispatch stacks, with everything's economically cleared, so Servum thought that those imports were priced more attractively than what Plexus was seeing on those imports.
Okay, I'm just wondering, because one of the things I think that we've been seeing in the last couple of years is that actually during that period, net imports, even on peak days in the summer, our net imports are actually going negative.
Yeah. Well, I think this is kind of a bigger picture item that you need to think about going forward. And I've been in discussions with CPUC for years on this, is better calibration of the external markets, that this shouldn't be an exercise of modeling the availability on the other side is perfect, because there's certainly a profile that the resource mix of the neighboring zones influences the availability of imports. So I think we need to move to dynamic calculation of the actual loads and resources of those zones, and not imposing an artificial constraint during this particular window. So if we have a dynamic calculation of load resource balance by hour, we've modeled the friction between markets appropriately, we can get a better picture rather than this profile that says we have opportunity to get 11 gigawatts in all these hours, and then it drops to 5 gigawatts, and then it goes back up to 11 gigawatts.
Does the modeling also model exports?
Yes. So the model will fully economically clear all resources. So to the extent the clearing shows a lower price in California than external, the model will allow it, subject to constraints that you define, will allow it to export during those hours prior. I mean, this may be the effect that you were talking about in the hours prior to the net peak. The imports dropped to zero. Whether that's a typical day or an extreme day, if we have enough solar resources such that even on an extreme day, we expect net imports to drop to zero. From an economic standpoint, you'd still keep all your energy limited resources fully charged before you start exporting. So I wouldn't expect that to drive the reliability result too much. But again, I still think making sure that you're doing that economic clearing in all hours of the day, rather than having a transmission constraint that's just predefined, makes sense.
Okay. have to think about that a little bit more.
Yeah.
We also have a couple online hands raised. First, we have Nick.
Hey, Kevin, Nick Pappas here. Thanks for this presentation, and I apologize, I missed everything except for the last few minutes because I had another commitment, but I wanted to ask about the heat maps. I think this is such a helpful way to visualize the sort of forecast, and I think Steve's question in the exchange just now sort of maybe hit on most of the key themes I wanted to ask about, but I'm curious if you have a take on, whether addressing some of those other limitations, whether it's energy limits from the West or energy limits from our hydro fleet, or any just kind of, prognostication about how these hours of risk might shift if we tighten some of those other potential risk hours. Like, would we be seeing wider bands, or any thoughts on what we might want to think about for scenario analysis here?
Yeah, certainly. So we do anticipate, in other work that we've done, anticipate that the evolving resource mix for the neighbors is going to influence that availability profile as well, that on critical days, we see them preserving their resources well in advance of the critical hours as well. So if we assume that we can get a full 11 gigawatt import, then your energy limited portfolio maintains full state of charge all the way up until hour 16, and then it starts dispatching. That's probably not realistic in some of the extreme scenarios. So I think we've seen that to be a driver that surfaces additional risk. So if I calibrate all those neighbors with their changing resource mix to 1 in 10, their contribution, they're also having to maintain an energy limited portfolio as well. And so maybe those constraints start to bind a little bit earlier in the day than hour 16.
Thanks, Kevin. That's really helpful. So you think probably extending earlier versus later?
Well, probably both. That I think the window probably expands on both sides.
Got it. Thank you.
Yep.
Next, we have a hand raised by Perry.
Hey, this is Perry Servideo, CISA. Kevin, thanks for putting all of this together. I had a question that popped into my head while you all were talking about this most troublesome hour moving between July and September, and the conversation that followed that. And you can just tell me if this is a completely dumb thought, but I was wondering if there's a metric involved here where we could somehow see whether the cause of the unserved energy is insufficient energy production earlier in the day, or lack of more and maybe longer duration storage capacity. And if that's a dumb idea, you just tell me. But it seemed to me that the core question is, if you were to stack in, another 10 gigawatts of storage, would you still see, the unserved energy, or is it actually a lack of charging energy earlier in the day?
So it's generally not a lack of charging energy. It's really a timing question of when do we start to have to discharge. We always have enough resources to fully charge the energy limited portfolio. It's just when do we start to have to discharge. So if we start discharging in hour 14 versus hour 16, that will make a difference on reliability. But we've got enough energy to get everything charged. When do we start discharging?
Yeah, no, that's really helpful. That's really insightful to hear. Thanks for that. I'm sorry, you were going on.
Well, just going to say that, the addition of any resource, 1 megawatt hour of energy in any of these critical hours is going to improve reliability. So yes, we could add 10 gigawatts of storage and it would help the situation. But if we're still calibrating back to 1 in 10, so we add 10 gigawatts of storage, we remove the effective capacity contribution of that 10 gigawatts, perfect capacity or load addition, then I would think you would see a further concentration of events in the energy constrained category. So higher the penetration of energy limited resources, more of the events at 1 in 10 will be driven by the energy constraints.
Yeah, it just seems though that, we all know there's the balance between how much solar you're bringing on and how much storage you're bringing on out into the future here. But it seems to me that if you had planned on more or longer duration storage, perhaps some of the EUE would be eliminated. Now, like you said, then you'd calibrate it because you want to get it back to a 0.1 LOLE. But thanks for the clarification on whether you were seeing it as a storage capacity issue versus a charging energy issue.
Yeah, and I hope you'll stick around for this afternoon because I think some of the discussion on accreditation will influence that or help kind of uncover some of the nuances there.
Yeah, I already have the popcorn in the pot.
Good deal. Kind of that there's a delicate line. So in work that we've done with E3 in the past is, recognizing that the ratio of solar to storage matters, and that if I get below this, the marginal value of storage can drop off a cliff. And so we're trying to keep enough investment in solar so that the storage maintains a high contribution on the margin. So you're certainly having to monitor all those, and then recognizing that storage's contribution, that if we surface energy constraints, there's a delicate balance there between capacity, contribution, and energy. And you can see that in all these charts that we're kind of at that nexus that some of our events are capacity constrained, some are energy constrained, and trying to balance that. I can't just convert this to say, all that matters is the duration of the batteries. Also matters the capacity of the batteries, and kind of that delicate balance between those two. We're kind of at that point, the mix that we have, we're capturing both of those benefits out of the batteries.
Yeah, that's fair. Thanks for that additional color.
Yeah.
We also have some hands raised in the room from Michaela and Noah.
Thanks, Michaela Fleck, Customized Energy Solutions. So could we get more insight or data into how often there are capacity constraints versus energy constraints for storage? Like, it's interesting that you see both, but like, do you see one more than the other, or?
Yeah, we could pull that result. I didn't pull that result out, so I don't even know anecdotally what that breakdown would be, but we could pull that.
Thanks.
Noah from Middle River, just following up on that, how do you look at this heat map to tell that it's a capacity constraint versus a energy constraint?
So I know it from looking at the detailed results of what events look like in hour 22 and events look like in hour 18 and 19. So it's not just from this, but you can see that there's a gap between hours that are read earlier in the day than later in the day. And that gap is, if you go look at the actual dispatch reports, you see that events where we had it in 18, 19 were capacity limited. We still had plenty state of charge. We just didn't have enough resources to meet the net load. And then the events that happened in hour 22 were driven by the energy shortfall. We had exhausted the storage.
Interesting. And when Perry suggested adding 10 gigs of additional capacity, that is sort of above your slide 57. There's already sort of surplus integrated into these heat maps that already gets you to a 0.1 or close to it, right?
Right. We pulled that surplus out for those heat map calculations. So we adjusted the imports down such that we're getting much less contribution from the neighbors, and then did those heat map calculations. So if we didn't have access to 2,350 megawatts in 26, then this was the heat map that we would get. But with that contribution, it'd all be green. That's right.
Right. And what is Okay, never mind. Got it. Thanks.
Yep.
Not seeing any further questions.
Comparison will be a scenario 3 and 3A heat maps from the October workshop. 3 shows very few events happening. 3A shows what a calibrated 0.1 portfolio events look like. I think what is interesting from my standpoint is as you go in time, you add the hour 23 into the mix of risk hours, and earlier, like it's the 16 through 23 or 18 through 23 are the consistent set of hours where we will be we are observing unserved energy events. Things change after nuclear retirements. That's where the additional hour is being added in 2033, 4 stuff. And as we think about accreditation in the afternoon, it is helpful for us to focus on these risk hours, if that's the approach that we want to take, because any 1 hour presents a picture that is very different than what the other hour is looking like. So yeah, we can talk more about that in the afternoon. Looking forward to stakeholder presentations. I think we only have 10 minutes and no more questions. Can we break early for lunch, Christina?
Yeah, we'll take our 1 hour break for lunch.
Okay. And we reconvene at 12:50?
Yep, 12:50.
Yeah, I want to come back at 12:50 because we want to allow enough time for the afternoon discussion. And our meeting ends at 3, so awesome. Thank you, everyone. Thanks, Kevin.
Thanks.
Everyone, welcome back. We're going to be getting started here with Aditya.
Thank you. This is not working. Casey, are you able to advance the slides?
All good now. Yes. Sorry about that.
No problem. Thank you so much. All right, so the exercises so far, we have we did a draft analysis that shows in Plexus, how do we get to a 0.1 portfolio? We will make updates like we talked about in the morning to some of the things, hydro, storage, storage rates, a little bit of review on imports and stuff. And once you have all of those numbers, we plan to put into the new Plexus model, get to that 0.1 portfolio again. Once you have the 0.1 portfolio, you have to develop a set of counting rules that which you apply to those set of resources in that portfolio, and then come up with your planning reserve margin. To be able to do that, there are multiple approaches, right? You can calculate your planning reserve margin on a monthly basis, seasonal, or an annual basis. You can accredit resources based on their performance in all hours, in a subset of hours, during the risk hours, during the hours of observed risk in your LOLE models. There are different ways of assessing risk and accounting for those risks methods. You can also have a program that is based on the gross peak. You can have a program based on net peak, or like the CPUC slice of day, you can have a 24-hour requirement. So there are different ways for us to think about this. We have not had a detailed discussion, so we've invited 4 experts to come present to us on their experiences on counting rules discussion and PRM methods. We will hear from 4 presenters today. Nick Pappas from NP Energy, Kevin Carden, Astrape Consulting, Power Gem, Zach Ming from E3, and Bedard is going to talk to us about the CPUC slice of day program and their LOLE work. The slides are presented. Feel free to ask any questions to our presenters. We have time until 2:45 to go through these slides and material. We will manage time as it goes along. Any general questions before we move to our first presenter, Nick?
Not seeing any questions.
All right, thank you. Nick? Nick has the slides that have some animation in them. So Nick, if you want to share your screen and walk us through the deck, we can move back to this later.
Thanks, Aditya. That sounds great. Hopefully you can all hear me well. Aditya, thank you very much for the invitation. Nick Pappas, I'm a consultant with NP Energy. my firm. Happy to be here today to share just a really high-level overview of resource counting options with some context around California's current programs. This is, again, very high level, but hopefully spurs some thoughts and questions as we get into the more complex, detailed technical issues in some of the presentations later from Bedad, Zach, and Kevin. So sorry I couldn't be there in person today. I really hope to, but I'm pulling double duty with testimony in another proceeding today. I needed to be available for that virtually. So let me go ahead and see if I can get my screen share up. Just a moment. I'm seeing, give me just a moment here. I'm getting an option to show not the full screen. See if I can get WebEx to cooperate here. All right. Does that work for everybody?
Yes.
Yeah, great. All right. So again, it's going to be just very high level. Let me just talk through some of the key themes we're going to hit on here. So just to highlight, resource counting is really foundational to compliance programs. That includes resource adequacy programs, capacity market programs. You could also extend resource counting to how we accredit resources for RECs or GHG or other values. In this context, resource accreditation is really referring to how we value the reliability contributions of specific resources. So I'm going to focus specifically on system resource adequacy. It's worth noting that there's different methods, or at least variations, for both local and flex, which I'm not going to get into here. But some of the key methods I'm going to talk through today are ICAP, installed capacity, UCAP, unforced capacity, effective load carrying capability, sometimes called effective load carrying capacity, both the average and marginal versions of ELCC. And then I'm not going to go super deep on slice of day profiles, how those are generated. We've had lots of good discussions of that in the CPUC RA program, and there's some presentations I can link to where that's been discussed, but I'll highlight how those sort of sync up with some of these other programs. And then I'll just talk through some of the sort of conceptual differences at a high level as well. So there's many ways you could parse these, but one big category that I want to highlight is sort of historical versus simulated resource performance, and the role of simulation and analysis to produce these. So increasingly, we're seeing simulations being really central to resource accreditation, which I think is certainly something that I support, helping us to really understand the full range of risks that the system could experience across whatever time horizon we're looking at. And then increasingly, we're also seeing resource accreditation consider interactive effects. So how different resources interact with each other to support reliability. So we just had a good discussion on this before lunch around sort of energy sufficiency and storage. I'll get into a couple examples in that same category. But first off, I want to contextualize this in the California programs. And I know this is a simplification. I'm specifically talking about the CPUC jurisdictional and the CAISO jurisdictional programs. I'm not going to get into any of the other public utilities or other areas, but specifically for CPUC and CAISO, we've got sort of three key reliability resource accreditation frameworks. Each are different methods and have kind of different intents and purposes. We always talk a lot about how we want them all to line up perfectly, and I'm going to try and talk through why that's a little bit challenging in the current construct, and maybe some options we have moving forward to help bridge some of those gaps. So in CPUC RA, we are moving to slice of day, which is a month-hour, so representative day program. So each monthly showing has 24-hourly values for each resource. For most resources, these are flat values, but for solar and wind resources and storage, they're either hourly profiles or other sort of systems for how we account for storage. This framework blends a few different methods, so ICAP in some cases, exceedance in some cases, and then we're talking about some new versions such as the sort of worst day serve and form profiles that are currently proposed, at least to be sort of directionally adopted at the CPUC. As we move into CAISO, we move from 12 by 24 to a 12 by 1. So similar to CPUC RA, there's 12 monthly showings, or year ahead and 12 monthly showings, so 12 values. The graphic here is the the current tech factors for solar on the 2025 NQC list. This comes from the slice of day gross peak hours, which we'll get into. And similar to slice of day, the CAISO QC list blends a number of different methods. So we have ICAP in some cases. We're, of course, talking about the transition to UCAP. We have exceedance, and we have other methods sort of embedded in this for resources like geothermal or hydro, which come out of CPUC decisions. And then finally, we have the IRP. So the IRP is sort of its own unique beast. The IRP is not a 12 by 24 or 12 by 1. I would characterize it as a 1 by 1. So in the IRP procurement track orders, the midterm reliability orders, each resource has one value per year, which is intended to reflect its marginal ELCC contribution in that year. So reflecting saturation and portfolio and other effects in the year that it's installed. There's also some other variations of resources that are not marginal ELCC, and then there's some subcategories, things like the Diablo Canyon replacement resources. So you can just look at these three graphics and see from a bare basic dimensionality standpoint, there's obviously going to be some differences in how these values line up. And then certainly between the two on the left-hand side, which are full portfolio accreditation programs versus the sort of single resource-specific valuation for the MTR, there's kind of differences conceptually in what's intended to be drawn from each of these values as well. All right, so I'll just briefly go through some of the ex post methods. So these are methods that use historical values to generate resource accreditation. The simplest one is ICAP, installed capacity. This refers to the nameplate value, and this would be, nameplate that it can produce with its interconnection, and then may or may not have other constraints like deliverability, sort of depending on the program. So NQC would reflect some of the other adjustments as well. ICAP is still in use for thermal resources. Most regions are moving away from ICAP and at least transitioning to UCAP, if not ELCC. That includes CPC and CAISO, where work is ongoing in this initiative and at the CPC to develop a UCAP proposal. And I'll just skip over into UCAP because I think this is where some of the more interesting action is happening. UCAP refers essentially to the expected availability of a resource during specific hours based on historical performance. And there's different ways to implement UCAP, but typically this would at minimum reflect outages, at minimum reflect ambient D rates, and I think would also reflect outages. There's a lot of discussions and different approaches to how you measure this over what period of prior years, what period of hours, what outages to include and exclude. But conceptually, you can see the D rate in the graphic on the right, showing the sort of expected variability, or expected availability. There's work in some regions to move beyond UCAP, specifically in regions with fuel scarcity risks or significant correlated outage risks, where you have, for instance, events like what happened in ERCOT with the Texas freeze, where you may have a lot of resources go on outage, either due to fuel or other forced outage issues at the same time. And those are unlikely to be captured in UCAP, which might be looking at a limited set of recent historical hours and may not reflect sort of the full risk that you're trying to address going forward. Finally, we have the exceedance profiles for slice of day. This is currently only applied to solar and wind. Exceedance is essentially a statistical method to translate historical performance into hourly profiles. So essentially to say, here's how much of a resource we can expect on X% of the time. We have created a construct for the CPUC to do this based on the worst days observed, so the highest gross peak days observed. There are ongoing discussions to try to better align this with ELCC analysis by using SERVM profiles and trying to identify the days that the SERVM model identifies as the at-risk days. ACP has put a proposal forth on that, which I've supported, and that appears at least to have directional support in the current CPUC proposed decision in track 2. Okay, I'm going to jump into some of the simulation methods. If you all bear with me, I'm just going to switch my headset because I'm getting some feedback here.
All right, can you all hear me okay?
Yes.
Great, thank you. All right, moving into the simulation methods. excuse me, sorry, I'm still getting over a cold here. And I think we're going to get a little bit more on simulation from Kevin and Zach in addition to what was shared this morning. Just at a very high level, generating resource accreditation from simulation modeling essentially requires 3 sort of key steps. Generating a data input set, so this is resource availability, load, probabilities of different events like outages, and then passing that through a reliability simulation model. So that could be SERVM or Recap or Plexos ST, excuse me. And then where it gets a little bit more complicated is how you take that analysis and translate it using tools into resource accreditation valuation. So here I have 3 different graphics from the IRP MTR order. So each of these represents a year of value for resources. These are the marginal ELCCs that you would take from that SERVM exercise. Excuse me. But you could also do this for monthly values. Historically, we've done this for monthly ELCC values in the CPCRA program, or seasonal values, which you see in some Eastern ISOs as well. All right, so I'm going to go through a couple of graphics here. I hope these come through reasonably well. But I'm gonna go through what I would call maybe a poor man's ELCC, so a really simplified representation of a day and how resource availability and saturation and portfolio effects look from the context of a single day. Of course, a real system model or ELCC analysis would take into a much broader range of conditions, but I think we can visualize some of the key effects using just a single day here. So ELCC is essentially a benchmark of a resource to its equivalent perfect capacity. There's many methods of doing ELCC. It can be done on a number of time horizons, and it can also be done on a number of different sort of allocation methodologies. So things like average versus marginal ELCC are sort of subsidiary to the broader ELCC construct of trying to analyze what a resource's reliability contribution is on a given system. I apologize. This is a lot more than I've talked since I got this cold. So on the right-hand side, we can see sort of a summer peaking system. This is just sort of data pulled from CAISO looking at a specific day. Without any variable energy resources, we can see that the peak hour is likely going to be the most constrained hour, the capacity constrained hours of hours ending 18 and 19 here. Once you start adding solar, we start pushing that risk period deeper into the evening. So I think folks are probably pretty familiar at this point with this kind of core saturation effect from solar. And you can see in this bottom graph how the average ELCC contributions of the solar fleet decline over time in this simple model as you go into the evening, going up to 10 gigawatts. And you will, I don't have this included here, but you will get to a point where the contribution of the next solar resource is essentially 0. So I'm going to try this graphic out. I'm hoping WebEx can handle it. We'll find out. Let me know if this is playing.
It is.
Let's see, here we go. So this is if we just sort of simulate this visually as we play out. You can see the capacity critical hours start to tighten into the evening, and this is just very much expected with if you only install solar on a system, we're just going to push these hours into the evening, and we're going to see less and less marginal value from those solar resources as we go forward. If we start adding storage, similarly, without solar resources, we're going to start to see that storage resource saturate and start to push beyond the 4-hour window that storage resources are currently typically set at. And we're going to see the capacity critical hours start to extend across a broader afternoon and evening period. And similarly, you're going to see the marginal contribution of each battery resource continue to decline. Now, of course, ELCC typically is set up to reflect that you've got a suite of resources on here. In this case, both solar and wind resources, or sorry, solar and storage resources. Excuse me. And in this case,
the solar and storage resources are very complementary. They have positive synergistic effects. And what you can see is that the solar fleet, as you add more and more solar, pushes the dispatch of the storage deeper into the evening, tightening the net peak, keeping that value up. And then similarly, the storage resource pushes more of the critical hours earlier into the evening rather than just that net peak period. Average and marginal ELCC, I didn't go too deep into this. I think Zach and Kevin may touch on this in a little more detail, but essentially speak to two different methods of assessing those sort of technical contributions that we just went through. An average ELCC will take the full fleet, the full resource fleet, let's say the full solar fleet, I'm sorry, I'm struggling here with this more than I expected. The average ELCC is going to take the full solar fleet, assess its entire contributions relative to a counterfactual, for instance, no solar, determine how much perfect capacity that provides on the system, and then allocate that ELCC across all resources in the solar fleet. A vintage marginal ELCC, sorry, I should say average ELCC, this is essentially the method that was used in the CPUC-RA program until slice of day. Vintage marginal ELCC essentially takes the ELCC in steps and tranches like the IRP MTR and will allocate each resource its marginal ELCC at the time of its installation. I'm so sorry, my voice is just totally gone here. What I would characterize as maybe capacity market marginal ELCC is the construct that's being implemented in Eastern markets is not a vintage marginal ELCC construct, but an ELCC construct which takes the marginal contribution of those resources and then applies the marginal value to all resources within that fleet. So if you get to a point where solar is fully saturated and provides no additional value, you will get zero accreditation, even if that fleet of resources is carrying some of the load. So this is just sort of assessing what this looks like across the two resource categories. As the risk hours shift later into the evening, you can see a sort of slower drop off of the average ELCC versus a pretty aggressive drop off of marginal ELCC as those risk hours shift into the evening. This is just for a solar only resource. So talking through how this works in California, we've got a couple of different data sets and methods here. So on the left-hand side, we have the CPUC reliability programs, IRP and RA. All of these start with resource data. The data is unfortunately not unified across programs. I think that's an area we could work together to improve. But we have primarily SERVM for both IRP and RA reliability programs. We have a 23-year historical data set for solar, wind, and load, which drives the majority of sort of analysis and simulation in addition to outages. And then CAISO is using Plexos ST with a one-year data set that I think is drawn from some of the similar historical data, but has some different dimensions than the SERVM data. And I have Resolve on here. Resolve doesn't really play the same role in the RA programs or the IRP programs, but it is sort of a parallel model with its own different data. I'm so sorry. I'm really struggling with my chest here. Okay, so finally, just to recap the different programs in California, just the dimensions of these and the differences. We have a sort of annual marginal program in the CPUC IRP midterm reliability requirement. We don't yet how the RCPPP is going to look. We have the month hour program and slice of day. Both of these use the same SERVM data inputs, but they use different approaches. And then the CAISO RA program, which is single monthly values using a different data set. I added, Aditya, if you'll indulge me, I added a couple slides just after the discussion with Kevin, just to highlight some of the, before lunch, to highlight some of the potential options that you all have here. I don't think there's going to be too many surprises in here, but just to contextualize sort of the current and future options for CAISO. Currently,
we are taking the gross peak hour from slice of day, or sorry, gross peak hour from the CEC load forecast, taking the exceedance value from slice of day and applying that. That's reflected a pretty big shift in the tech factors from ELCC. We've potentially discussed some movement towards net peak, so you can visualize just sort of how that would shift into the evening. I think this is pretty straightforward. I think where this gets much more complicated is when you start to sort of integrate and understand how storage fits into this mix. So the discussion before lunch, I think, was really helpful to just highlight that we're sort of at the edge of a few different constraints with storage. We have capacity constraints. Can we hit the capacity limit at any given hour? And then as storage is installed and we start to saturate, it becomes less about capacity and more about the storage energy, which dispatches over a longer period of time. And so you may move, rather than being in a net peak world, to actually being in a sort of multi-hour constrained world based on how the storage is operated and constrained. And then you can add even more complexity if you get into a world where the system is energy constrained, where it's not just the the net peak hours, but the whole system needs energy to fill the storage resources and sort of reduce the storage dispatch. Now, we're probably not moving into that world anytime soon based on the results we just saw, but we could be in a specific, very bad hydro draw, or if things change dramatically in the West and we see sort of data center load growth skyrocket, we don't have, I think, as clear of a sense of exactly where we're going across these constraints as we might have had in a simpler energy system a few years ago. And with that, I'm gonna I think stop before I cough anymore and hopefully catch my breath for some questions, either now or at the end. And I'll Aditya, I'll pass it back to you. Thanks, and apologies again for all the coughing here.
Hey, no, thanks, Nick. Appreciate it. And if you want to send us these new slides, we can get them added to the deck and repost. I'll try to give you a breather. If you'll hang around for a little bit longer, then I will
Yes.
move to the next presenter. Thanks, Nick. Evan?
Appreciate it. And good presentation, Nick. A lot of the same material that Nick covered is in this deck. I think it's good to reiterate some of the concepts that he laid out, but I won't spend too much detail unless I get further questions on that. I will try to hit on some of the objectives in a little bit more detail in terms of what you're trying to accomplish with the different accreditation methods, how you kind of get alignment between PRMs and ELCCs and all that. So, and then some kind of specialized or some very nuanced criticisms of the various methodologies that are presented. Not here to endorse any particular method, but recognizing that all of them have some shortcomings and all of them have some benefits. So similar to the intro that Nick gave, ICAP, PRM, if I think about what reserves are for, kind of several main components, we have reserves for operating reserves. So we keep capacity reserves so that we have access to those reserves during critical days. So if we're carrying that 5-6% reserves, we got to have some capacity in reserves for that. We have reserves for economic forecast error. Load grows faster than expected, slower than expected. There's some asymmetry there. We need to carry some reserves for that unexpected load growth. And then we carry reserves for weather variability. So if I think about my reserve margin, those three components obviously drive it. Regardless of the accreditation methodology that you have, you got to carry some reserves for that. The final component is generator performance. I've listed it as outage risk. With energy limited resources, non-dispatchable resources, that performance risk is more than just forced outages. There's other things that go into that. But from an ICAP standpoint, that's how we would build our reserve margin, is those things layer in and result in the need to carry, in this example, a 20% reserve margin. If I move to a PCAP reserve margin, I still have to carry reserves for weather variability, economic forecast error, operating reserves. But I've reduced that outage component that those resources, we don't have to carry reserve for that because that's embedded in the accreditation. So that 4% impact says, all right, that 100 megawatt resource is really only providing the equivalent of 96 megawatts of perfect capacity. So I can strip those 4 megawatts out and reduce my PCAP PRM. So when I talk about PCAP PRM, it's always lower than my ICAP PRM, not because we need fewer resources in that environment, but because we're hitting all the resources with a D rate. Everything gets cut from its installed capacity rating to get us to this PCAP PRM. Now, I skipped the unforced capacity accreditation in here, jumping straight from ICAP to PCAP. There's an intermediate step where you could do UCAP, as Nick mentioned. And essentially, the approach for that is generally take your ICAP megawatts, reduce it by E4D. So ICAP times 1 minus E4D will give you your UCAP accreditation. That's historically been the context. So a 100 megawatt generator with a 4% E4D would get 96 megawatts of accreditation. Now, the concern that's been raised with that is that how we expect the resource to contribute to reliability? It's E4D. Well, what happens during most reliability constrained days? They're generally driven by some combination of extreme weather, but also poor unit performance. The units are not operating at their expected reliability on critical days. And I've just taken a snapshot here from one Servum simulation run. What is the percentage of the thermal fleet that's on outage across the year? And on average, it's the dotted blue line down there at the bottom at 3%. But the 75th percentile, the 95th percentile, the 99th percentile shows many more outages than average. And those are the times when you actually have reliability risk. So what credit should a thermal resource get? Should it get the 3% number, that hit, or should it get hit by something larger? So this is the argument that we've made, moving straight to PCAP, going ICAP to PCAP, because then the resource, its actual contribution to reliability will get assessed instead of this average outage rate, which doesn't necessarily correspond to its contribution to reliability. And I'm stealing from E3 here. We've worked pretty hand in hand with E3 on a number, and I think Zach's going to show the same chart here in a minute. But we've worked on a lot of the same concepts and a lot of the same jurisdictions, and I agree with a lot of the characterization of the various concepts and methodologies. So I wanted to borrow this, and I gave the proper accreditation here to Zach. Appreciate this, but just thinking about the evolution of capacity accreditation. So 20 years ago, when we started to introduce wind and solar, you would look at, well, what's the typical output during the afternoon hours? And if I just look at typical output during afternoon hours, and there'll be a tie to exceedance here, but typical output during those hours, maybe 30, 40, 50, I mean, in ERCOT, look at 75% solar output during the gross load peak hours. Why does that not work for accreditation? Well, if we get enough of that resource, we've shifted the net load peak to a different point in time. So continuing with this window, this is the hour. I'm just going to measure the output during this hour. Well, it's no longer consistent with the time that reliability is a concern. The average ELCC actually addresses that in that we're only giving it credit for the reduction from the gross load peak down to the net load peak. So it doesn't have the same inherent problem that this availability during peak approach has, but it still is capturing the full change from the gross peak down to the net peak. And so that slower decline in average ELCC relative to the marginal, is that a perverse incentive for new resources coming on the system? That's been one of the criticisms of average ELCC, but it is fully reflecting kind of that gap from gross peak down to net peak. And then marginal ELCC is just a measure of the output during critical hours or the output during the net load peak. So this is a bit simplified because conveying exactly what it means by critical hour, it's not just unserved energy hours, and it's not a binary, it is or it's not a critical hour. So there's a lot of challenges, but I think conceptually this is a great way to visualize the evolution and accreditation concepts over time. All right, Let's talk about average accreditation for a minute. So this connection between the PCAP reserve margin, ICAP reserve margin, with average ELCC accounting, it doesn't matter what your resource mix is, you will have the same PCAP reserve margin. So I could have 100% solar and battery portfolio. Obviously, I would need tons of capacity in order to meet the 1 day in 10 standard with that. But if I do, then I've got in this example, 116% or 16% PCAP PRM. If I did it with all thermal, 122% ICAP would still translate to a 16% PCAP. So by definition, the entire definition of average ELCC is take your whole portfolio, do ELCC, just take all that out and put back in PCAP. But by definition, your reserve margin is going to remain static with average ELCC. So it doesn't matter what the resource mix is, it's agnostic to that. You'll always maintain the same ELCC. So it achieves at least one objective of having some stability. It has other challenges in terms of calculating. How do we do that synergy calculation that Nick hit on before between solar and battery? But from a portfolio standpoint, regardless of the resource mix, we'll always get back to the exact same PRM. So that would remain stable. The only thing that could change that would be changes to load variability or changes to those other components we talked about before. But from a portfolio mix, it's agnostic to the portfolio mix. So this is the challenge for average accreditation, is how do we give credit? So we could use a vintaged marginal approach that as each solar resource gets added, then it gets its ELCC. But then you have these questions, all right, the order in which I build out the system matters. And so the first solar gets a lot of credit, and then it gets very little credit as we've shifted the net load peak to late in the day. And then we start to add solar. It actually makes that, as we add storage, it actually makes that solar more valuable. And so who gets credit? So we've done various surfaces that just proportionally, take the entire portfolio and accredit all resources proportionally. So if I do this calculation for a 1% slice of the portfolio, a 2% slice, and I build up the entire portfolio, everybody gets proportional credit to their contribution. So if I've got a 50 gigawatt solar portfolio in California, 10 gigawatt wind portfolio, and a 20 gigawatt storage portfolio, I would do the assessment for a small slice of that, build that all the way up to today's portfolio, and the integration of those marginals would give you the average accreditation that each resource class has. Now, it's obviously the math behind that's fairly complicated, but it would at least, if you went that approach, you would keep that consistency, the static PRM, all resources. You're baking in the synergy in that accreditation concept. Let me just point out here, though, that if we are looking at marginal accreditation, so which direction, if under average accreditation, your reserve margin remains static, if I do marginal accreditation, which direction is the reserve margins, the PRM, going to go? It's going to go down because now our critical hours get shifted to later in the day when the net load is lower, or the actual load is lower, and so the sum of all the resource contribution in those hours is lower, and so you're going to have a declining ELCC based on declining PRM based on marginal ELCC. What's the direction that everybody is going? Most folks are moving toward marginal accreditation. So MISO, the DLOL approach, this is really an output during loss of load hours. It's a direct loss of load. It's intended to be a proxy for marginal ELCC, but you can get all the answers out from one run. SPP continues to use average. So we've got ERCOT's there's not really it's an energy only market. They're talking about various reliability incentive programs, various ways to credit. It's a performance credit mechanism, gives credit for output during reliability hours. What does that look like? It looks like a marginal accreditation. And slice of day, already heard some discussion on. I'll speak to that in a little bit more detail here as well. All right, so how does slice of day fit into this? So the idea with slice of day, this is really a communication tool from my perspective. You're going to hear some of my own opinions on slice of day, the benefits that it brings and the cons that it brings. But slice of day, essentially, we still have to run our reliability simulations and get to a 1 day in 10 reliability standard. So I'm building a portfolio that meets the 1 day in 10 standard. And then how do we accredit that particular portfolio? So we take the simulated portfolio and I plug it into, in this example, an Excel spreadsheet. And I look at how much could I scale that load? And I recognize that there are other approaches, more nuanced approaches to this, but a simple concept here, I scale that load until the resource portfolio that I have is not able to satisfy that load. So I've started from the green line, I've multiplied the load every hour of the day, scale that up until I exceed the capability of the system to serve that. So it could be a capacity shortfall, could be an energy shortfall. So I'm scaling that up such that this portfolio, without any outages, is able to satisfy that particular requirement. So embedded in this is, all right, that load profile is an expected load. I don't have any outages on the thermal fleet or the battery fleet in here. Perfect foresight to shave the peak. But essentially, it's just a test after the fact. We've already met the 1 day in 10 standard with this portfolio. Let's plug it back into this workbook and see, all right, what multipliers, how much could we increase load and satisfy with this? So that 22% recognizes, all right, this portfolio is providing reserves for all those things we've already talked about: weather, economic growth, the need to carry operating reserves, and generator performance risk. And so that's a way to convey exactly what this 1 in 10 compliant portfolio is supplying to the market.
Evan, we have a question in the room.
Yeah.
Steve Keen, Edison. It looks like you're just increasing it. Is it constant in each hour, or are you doing is it like a percent of the load in each hour?
Yeah,
or what?
yeah, in this example, it's a percent of load in each hour. So it's a multiplier. So the same multiplier for every hour. And so then the hour that's binding, not all hours are obviously binding, but we have to at least carry the 22% in all hours of the day in order to satisfy the worst hour.
Okay.
All right. So the concept, and I realize I haven't provided a ton of context behind marginal accreditation, average, but one of the arguments for marginal accreditation is that it sends the right signal to the marketplace. The point, I'm not going to try to go through all the details in the math here, but I want to emphasize a point that I made before lunch, that storage provides a mix of capacity and energy. Right, so there are days where we have capacity constraints, there are days where we have energy constraints, so we exhaust the storage. But how do we incentivize the right set of resources in order to solve both of those particular constraints? So in any given system, especially as we go forward, we don't need all 4-hour batteries. We're probably going to need some really long duration batteries and some short duration batteries. If I think about the first tranche of batteries that I add to the system, it's probably cheapest to add 1-hour batteries. Their cost per kW year is lower than adding a 50-hour battery, right? So I can add really short duration battery for cheaper. So that should be the first resource that I add from a total system cost perspective. And then as I need more and more resources, I recognize the next one has to run for more hours, and the next one has to run for more hours, the next one has to run for more hours. So I need to extend my duration for each marginal resource that I add. Now, if I send one signal to the marketplace, I say, all right, the marginal need is based on energy constraints. In this example, it would say, all right, the 4-hour battery at $100 a kilowatt year is fully satisfying that. That means that the 1-hour battery has a 25% ELCC. I realize I'm going to lose some people in the math here, but with 4 hours setting the margin, the signal that gets sent to the marketplace is, I need 4-hour storage at $100 a kW a year, or 1 hour is only going to get credit for $25 a kilowatt year. ELCC times the clearing price gives you his revenue. You end up with a suboptimal portfolio in this example because the 1-hour storage needed $50 a kilowatt year. So it's not as simple as, hey, I need energy or I need capacity. There's a mix of these, and you've got to send appropriate signals so that you get the right mix, not just try to look at the either marginal need for energy or the marginal need for capacity. So challenging concept, but ultimately we're starting to recognize that there are some nuances to any of these individual approaches that may not capture kind of the full implications.
There's a question in the room.
Yep.
No, Tom from Middle River. I know this is probably very illustrative, and I'm just trying to figure out the calculus sort of in my head.
Yeah.
Does sort of the minimum requirements within the RA space for a 4-hour duration product for capacity purposes, change sort of how this looks overall, or is it? I mean, granted, maybe the top portion is just really like a 4-hour battery, and then you get to a 6-hour battery or an 8-hour battery. Maybe that's is better example rather than a 1 hour or whatever it is. But does that change the calculus?
Yeah, I think you probably don't surface this that much if my calculus is just between 4, 6, and 8-hour batteries. The scale, the benefit of scale doesn't change that much from 4 to 8 hours. When we start to see this effect be more prominent is when we start comparing 4 and 8-hour batteries against 50-hour batteries, a completely different technology, where the cost for energy in those is much lower, but the capacity is still high. So then when I'm trying to balance between energy and capacity, it becomes much more challenging to take one single number and give credit to storage resources and get the right resource mix in. So if a 50-hour battery costs twice as much as an 8-hour battery, it may still make sense, or it still makes sense to buy a lot of 8-hour batteries because their capacity cost is lower. But you need some 50-hour batteries. So getting the right mix, ultimately it's more complicated than sending a single price point, I think, to get the right mix, or a single ELCC number. And not trying to create a debate. Zach and I have debated over all these concepts over brisket. Probably the last time I had brisket was debating this with Zach. So certainly there's difference of opinion on a lot of these concepts, but ultimately we see that we know that with solar and storage, you add penetration of those, you're going to get a declining ELCC. Right? So higher penetration, we're shifting that load peak out to later in the day, or we create the need for longer duration, so there's going to be a declining ELCC. The driver of that is that those are correlated contributions. So storage, big portfolio, it's all correlated. Solar, it's all correlated. It pushes the net load peak to late in the day. Now with uncorrelated outages, you actually have an increasing ELCC. So the marginal ELCC will increase as a penetration of uncorrelated resources grows. So if I think about that for thermal resources, if I had a very small system, an island in the Caribbean, 1,000 megawatt system, I got 2 generators, what reserve margin do I need for that very small system? I need a massive reserve margin, right? If I get a 100 gigawatt system, even if those generators had a 5% forced outage rate, I still need a really large reserve margin because one of those goes out, I'm short. I need a big reserve margin. I go to a really big system, I got the diversity of outages, my reserve margin, what reserve margin do I need? Well, it's going to be much tighter because when one generator goes offline, it doesn't necessarily bring the system down anymore. So I can plot that out here. I've done the math on this for a system size starting at a couple thousand megawatts up to 70,000 megawatts. The marginal ELCC is increasing because of that diversity effect. Uncorrelated events, increasing marginal ELCC. So if I look on the margin, I'm going to give credit on a marginal basis. CTs might get 1 minus E4D. That might be their actual contribution. But when I shed load, I've still got more than average resources offline. And so the contribution during critical hours is actually much less. So that's where I come to kind of endorse or embrace the output during critical hours approach, because I think that it reflects, all right, how is this class performing during critical hours? Well, it's really, in this case, for uncorrelated resources, it's the average ELCC. For batteries And solar, we've pushed it out. The output during critical hours is really the marginal ELCC. So it's really a blend of several different concepts that gets you to the right concept. But I think the framing of output during critical hours is easy to communicate. It provides that transparency. All right, if you perform well during critical reliability hours, then you're going to get credit for it. This could show up in things like shaft risk. So a really large generator, he may drive those events. He may get less credit than his E4D, but a small generator may be more correlated, and so it might be E4D for him. How do we actually do this in Serv-em? So I'll make a tie back to the DLOL just to show how kind of it simplifies or gets us back to this answer a little bit quicker. So we've got to do this for every class of resources or individual resources where we get the system calibrated to 1 in 10. We remove a renewable resource that will make reliability worse. And then we reduce load or add perfect resources to get back to 1 in 10. That ratio defines the ELCC. You can see how challenging this problem is, though, if I've got to simulate thousands or dozens of different classes of resources at different penetrations. Got to run a lot of runs in order to get that ELCC calculation for every resource. DLOL is an attempt at simplification by just measuring what's my output during critical hours. And so from one run, I can get essentially the same information as I would from an ELCC for every individual class simulated separately. So in Serv-em, we produce a number of metrics that give you that insight. I think it'll be something we'll explore in future work with CAISO is, all right, for each one of these portfolios, how did each resource class perform during those hours? And we can report that during gross load peak hours, net peak hours, high net load hours, or during unserved energy hours. So different ways of looking at your performance during the times that mattered. The marginal reliability impact, how much did a resource reduce unserved energy relative to what a perfect resource reduced unserved energy? So some different ways of getting to the answer a lot quicker. ELCC calculations, running these surfaces that we look at here, you got to run dozens of combinations, do a lot of sophisticated math in order to get back to a, smooth that out into a surface to kind of present how that looks with synergistic relationships between resource classes. But again, with this approach, we can get all those results out from a single set of runs. All right, I know that was tough math for right after lunch, but hopefully you guys got something out of that.
Right. Noah has a question.
So going back to the PCAP, and I've heard this in, I think Energy Division or PUC IRP space. Do you recommend using a PCAP for purposes like the ISO's default PRM type of requirements, or for the tariff as well as instead of like UCAP and so forth?
I do. I think that a PCAP methodology, it's the ELCC for all resources, and so it's the most equitable approach. So my perspective, my own personal opinion, I think a PCAP approach is appropriate.
So mainly, on the PCAP PRM side, it sort of fixed. Do you generally get a fixed PRM sort of forever, and all you're really doing is adjusting the QC values on an annual basis to reflect and get back to that particular PCAP?
That's right. A couple of caveats to that, though.
Okay.
One is if the load composition changes over time. So if I add a bunch of data center loads, all flat blocks of load, the reserve margin may change with that. So if I add all flat blocks of load, I got no variability. I don't need to carry reserves if I have no variability. But it's harder to serve DC load because it's around the clock. So the ELCC will go down. The PRM may also go down because less variability. So the load composition matters, but it'll be much more stable. The PCAP PRM, you can imagine it staying stable, subject to load variability changing over time. And then the other question is if you use marginal accreditation, even under a PCAP instance, because it's all done on the margin, then your PCAP reserve margin requirement will go down because the generally it will go down because the time of those events are when the net load peaks lower. We've shifted the net load to later in the day. So the load during that critical hour window is lower than it was at gross. So the PCAP reserve margin will go down as you increase the penetration of those energy limited resources. Thanks. Yep. Question?
Emmy Stenset from Midway Sunset. Not so much a question. I think you touched on this, but it's interesting to note that on slide 98, just as the 1 hour storage needs to be compensated higher per, has higher compensation as the number of thermal units goes down and is only used 3 to 5%, that also needs to be compensated. And on slide 99, as you point out, if we look at which resources to keep, it's interesting to realize that you need to keep, that it might be better to keep more smaller units, thermal units, as opposed to several enormous ones because of the uncertainty that one outage could cause. So just observation.
Yeah, so that's right. I mean, you do want to distinguish for the impact that a large unit has, but talking about a 1,000 megawatt unit with a 1% forced outage rate, that's probably still better than 100 megawatt units with a 10% forced outage rate. So all that's got to be normalized for and accounted for. Can you reiterate your comment on here about the conventional fleet for slide 98 here? Didn't quite follow.
Well, you were talking about correlating outages to the ELCC, and I was just realizing for the first time that a critical unit that goes on outage and it has several hundred megawatts, that creates a lot of uncertainty, whereas
yeah,
it's just a balancing act.
Yeah. With respect to the 1 hour storage, so I mean, the concept here, I guess I didn't tie it back to thermal resources on this particular chart. Just curious was.
Well, the anticipation is that the thermal resource, I heard Steve say that in 2045, they were anticipated to be, thermal units would still be here, but only be used 3 to 5% of the time.
Yeah.
Which means that they're at the top of that peak, only used as really critical. But as he pointed out, we have to find a way to keep them around so that they will be there for that. And that means each megawatt will be expensive.
Well, so on a day like this, we would actually still use those, if they don't have energy constraints, we would still use those resources around the clock. But this is 1 day in 10 years. So recognizing resource adequacy, high impact, low probability, those resources, even though they are a 3 to 5% load capacity factor, we need to have full access to those on these particular days. So they would come in at the bottom of the dispatch stack in this particular example.
Good point.
In order to keep the storage resources available for the critical peak.
Thank you.
Yeah.
We also have an online hand raised by Perry.
Yep, go ahead, Perry.
Hey, this is Perry Servideo, CISA. Thanks for all of this, Kevin. Really great stuff. You talked a little bit about well, I guess a lot about the synergistic effects between the solar and the storage. And I was just wondering in what you've been working on, if you found, I'm imagining kind of a world where every resource is on, say, like either a marginal or an average ELCC. Have you found any other synergistic effects between different resource types and storage, say storage and even like thermal, that might be worth mentioning?
Yeah, I mean, I think we've found something similar to what Mark showed earlier, that there's synergy between solar and wind, even that wind output, solar output tends to have a little bit of diversity. And so you get some benefit there between solar and wind. I mean, the thermal and storage resource portfolio, we actually see some negative effects. So you think about adding a big storage portfolio. One of the things that we've seen is that even if I model like a storage resource that dispatches as the very last resource in a stack. Even if it has 1,000 hours of storage, the dispatch order matters because and if I have to charge that resource leading up to the peak, then I've got this antagonistic effect that at hour 4, 5, 6 o'clock in the afternoon, I may have to run the thermal fleet in order to charge up the battery. So by running the thermal fleet, I introduce the potential for additional outages. And this is potentially, a disconnect between how Servum does it and Plexos does it, that we try to recognize those interactions within the simulation where we don't fix the forced outage profiles. We let the changing portfolio mix influence how the rest of the fleet will perform. So 4, 5 hours, 4, 5, and 6 in the afternoon, we have to run the thermal fleet. It creates new outages, and that means that they are unavailable now for the net load peak. So even though that storage got charged, now at the critical hour, that thermal resource is no longer there because the storage made it operate too early. And that ends up showing up as a reduction to the accreditation of the storage. So the storage, no forced outage rate, if I model it with no forced outage rate and really high energy limits, I could still get a 95% accreditation because of that interaction between the thermal fleet and the storage.
Sure. Yeah, I think I follow. Yeah, that answers the question. I was really curious about any other of the synergistic effects and how that flow into the ELCC values. Thanks for that.
Yep.
Yeah, Doug Karpa, Peninsula Clean Energy. I noticed one that, like both of these analyses and Nick's presentation as well, sort of takes as a starting point like 0 thermal, 0 solar, and like works up from there, and assuming everything else is thermal. But as we move to grids that are predominantly renewable, and one of my questions that kind of keeps coming back to my mind is like, presumably at some point the ELCCs for solar and storage come back, right? As you, like if you get to no thermal at all, obviously solar and storage are doing everything, and those ELCCs are going to be quite high. And so I'm wondering a little bit of, what do those analyses look like as we project out in the future with a lot of thermal retirements, or at least they're being used and dispatched less? How does that look? Because one of the ongoing concerns that we have, of course, is that ELCCs are really, really sensitive to what's in the mix. And that's very hard to predict on the 20-year time frame. And so it's a very black box. And for us as, we're contracting for this stuff, and it's like, well, the ELCC could be really high. It could be really low. We have no way to know. We don't know how to finance that, right? So it's kind of a mess.
Yeah.
From our perspective. So I'm wondering if you can talk a little bit about how sensitive, or what does it look like when we get to that, which we're quickly getting to, where thermal resources are falling away and the workhorse really is solar, storage, wind, maybe some geothermal. What does that start to look like?
Yeah. All right. So layered set of questions there. Yeah. So there are certainly inflection points. I'm going to talk about storage first. So there are inflection points in the ELCC, and that's made it difficult for people to forecast ELCC. So there's some opportunity or need for short duration, kind of daily cycling. And so in California, with a static solar penetration, maybe that's at 10 gigawatts of 4-hour storage, you get certain contribution. Then it falls off a cliff. You go from 80% ELCC down to 30% ELCC because you're kind of shifting the usage pattern. It's not just daily anymore. It's, I need to shift from weekend to weekday, or then from seasonal. And so you get these kind of natural cliffs in the in the storage ELCC curve. Now, if I layer in solar with that, then solar kind of props up, or it keeps that storage value elevated for longer. We've kind of talked about that synergy several times here already. And we did a kind of a surface in prior work with E3 that looked at, all right, I've kind of got this curve that with this particular mix of solar and storage, we can stay at roughly a 75-80% ELCC for 4-hour storage out to pretty far into the mix. But eventually you're going to exhaust the capability of solar to do that. Now, it is interesting that solar, if I think about solar's drop off now, so solar, as we shift the net load peak, if I had no storage in the system, we would eventually get to 0 contribution from solar. because all of your peaks would occur after sunset, and there would be no value to solar whatsoever if there was no storage in the system. Recognizing that we do have storage in the system, to the extent you are still operating solar, you still need the solar during any discharge window for the storage, it can still provide capacity value, still have a positive ELCC. So we have started to see that in these really high penetrations where we start to get energy constrained, that the solar ELCC, it may have dropped to 4, 5, 6%. It starts to come back up because now the solar, even though all your events happen after sunset, the solar is still keeping that battery charged until later in the day. It allows you to delay the discharge hours. So that's kind of where you start to see the solar pick back up. Eventually, though, the capability of even 100-hour battery, you're going to exhaust the capability of that set of resources pretty quickly to provide meaningful ELCC. When we think about in that context as well, 100-hour batteries, there's an opportunity for weekend to weekday shifting. But beyond that, if it's seasonal shifting, if I'm charging the solar in the summer and shifting it to the fall, how many cycles am I using that for? Maybe 2 cycles a year. It becomes extraordinarily expensive. So I like to keep in mind kind of the distinction between what's my penetration from an energy standpoint. So I can serve 95% of my total energy needs from combination of solar and storage. But from a capacity standpoint, you're still going to need a significant backlog that's going to run in this 3 to 5% capacity factor in order to keep the lights on. Any other questions?
Not seeing any other questions.
All right, thanks.
Thank you, Kevin. Want to go there? Next up, we have Zachary Ming from E3. Thanks.
Perfect. Okay, hello everyone. My name is Zach Ming. I am a consultant with E3. We're an energy consulting firm, and I'm based in San Francisco. We have offices across the US, and I'm talking about, like everyone else, accreditation. So I'll try to focus on the non-repetitive portions of this deck. Although for better or for worse, you'll see a lot of familiar graphics here. And I'm going to talk a little bit less about all of the options and a little bit more about what I think the right answer is, which is a marginal ELCC approach, or equivalently what I would describe as a critical hours reliability approach. So that I think is one component of a sustainable, when I say sustainable, I mean a resource accreditation framework that will stand the test of time. So setting up a resource accreditation framework that will be robust no matter how loads evolve in the future and how the resource mix evolves in the future. I think if that's the objective, there are 4, I think, key components of setting up a resource accreditation framework that can achieve that. The first is to utilize probabilistic modeling, or what also is called loss of load probability modeling. We've been talking about that today. That's not really the topic of this presentation, but I think using a model that can capture probabilistic variances in resources and loads is critical for accreditation. The second is accrediting resources based on their availability during critical periods. And I'm going to talk and precisely define what critical periods are. They're very closely related to loss of load periods, although they're not exactly aligned with loss of load periods. The second, and this is a little less meaningful within the CAISO context, because CAISO is not running a capacity market like many other ISOs, but however you accredit resources, you need to make sure that they actually show up in the market consistent with how you're modeling and accrediting them. You're not just running a back-end model and then hoping and praying that they show up, actually having some type of mechanism to ensure that resources show up. generally holding them financially accountable for doing that. And then a final point here, somewhat underappreciated, trying to do these things in the simplest way possible. I think that is incredibly important, both for the entity running the market and performing all these calculations, and also for all the market participants who are trying to understand and then respond to the signals that are being sent by all of these calculations. So making it understandable, transparent, simple. But today, mainly what I'm going to focus on is the second part there, which is accrediting resources based on their availability during critical hours. So the CAISO is by no means unique in taking a really hard look at accreditation. Every ISO around the country is also doing this. If you look at 3 ISOs that have made recent changes to their accreditation frameworks, which is New York, PJM, and MISO, they all have one thing in common, which is that they are moving to a marginal ELCC framework. They all kind of call it something different. New York calls it a marginal reliability improvement framework, MRI. MISO calls it the direct loss of load, or DLOL method. And PJM actually just calls it a marginal ELCC method, but they're all the exact same thing. They're all measuring resources accreditation based on their marginal contribution to system reliability, which is the exact same thing as saying their availability during critical periods. So I think to introduce the concept of critical periods, it helps to start with the traditional electricity system. And in the traditional electricity system, we had a load profile, and then to simplify it, we had a bunch of firm resources. And in this framework, the most challenging reliability periods were peak loads. And because of that, the whole resource adequacy framework was oriented around the peak. And it made perfect sense, right? Because you could say, if I can meet reliability during peak load, then definitionally, I can meet reliability needs during all of the other non-peak hours. That was kind of inherent to the makeup of the portfolio, which was a bunch of firm resources. Another way of saying this is getting more, this system, you could add more resources in this system that are only available at night. It doesn't change the reliability of the system at all. You could yank the load up or down at night. It wouldn't change the reliability of the system at all. So the behavior and availability of loads and resources outside of these peak hours or critical hours have no bearing on system reliability. It's only the peak hours, the loads during those hours, and the availability of resources during those hours that are influencing system reliability. And so that's why the historical paradigm was completely oriented around the peak. So Kevin already showed this slide, but I won't repeat what he said, right? But there's kind of, when everything was oriented around the peak, there was this desire to say, well, let's just measure every resource's availability during the peak. And that's when we had very low penetrations of renewables. That's exactly what happened. And then Kevin explained why that first availability during peak just kind of breaks down for obvious reasons. We moved then into an average ELCC framework, which measures, if you don't have any renewable resources, you have to build firm or dispatchable resources up to your gross peak. You add a bunch of renewable resources, then you only have to build dispatchable resources up to your net peak. So quantifying the aggregate reduction in dispatchable resources in that framework is average ELCC. And then marginal ELCC, I will actually explain marginal ELCC on this next slide right here. So this is taking the same framework of a simple day, but in a system with lots of renewables and storage on it. What you can see in this system, we've added a bunch of renewables and namely a bunch of solar. What you can see is that during what was formerly the peak hours of the system that were previously driving reliability needs, we now have an abundance of energy, meaning that peak hours in this system are as irrelevant to system reliability as nighttime hours were in this system. So because of that, it actually doesn't make sense to really even care about the peak anymore at all. And so with kind of that backdrop, you can kind of, free yourself from the peak and start to think about what should the total capacity requirement be and how should resources be accredited under the system that exists right here. And what we can do in this system is we can say, well, the hours that actually matter for system reliability here are highlighted as critical hours, which are hours when essentially there's loss of load or some risk of loss of load. And the total capacity requirement of the system is just the average of loads served during that period. And the accreditation of resources for this system is their average availability during those same critical hours. And definitionally, those will equal each other. The sum of the average availability of all of the resources will equal the average of loads served during critical periods. So there's a lot of takeaways that we can kind of look at from this system. I already covered the first one, which is that in a very high renewable and storage system, this is almost certainly not going to be overlapping with peak loads. And you can see that, in fact, the capacity requirement, if you look at the height of the stacked bars on the right, it's actually lower than the peak. And so in a high renewable, high storage system, the capacity requirements on the system in a marginal ELCC framework or critical hours framework are going to be lower than the peak, and that's fine. The second thing I will say is that it's a little bit challenging to identify the critical hours. So here you can see critical hours are highlighted by loss of load hours. But that is very much a function of how storage is being dispatched. If you look at this, the way that storage is being dispatched in the system, in the very first hour of the critical period, it's actually dispatching at a relatively low level. And then storage dispatches ramping up over the next few hours. That means it actually has the capability in that first hour to completely eliminate loss of load in that hour if it wanted to. Now, by doing that, it would leave less energy in the tank, and loss of load would be, in some of the later hours of the critical period, would be larger. So there's no free lunch. There's a decision around how storage is dispatched and what the resulting loss of load looks like in how you dispatch storage. The way that storage is dispatching in this particular system is to minimize the depth of loss of load. So it has many loss of load hours, but it's a very shallow loss of load event. That's a very different outcome than if storage were to use all of its charge up front and then be left with a shorter event, but a much deeper event. Now, it sounds like this, one takeaway is, well, we should really be focusing a lot on storage dispatch. One interesting thing about critical periods is that the way in which storage dispatches has a very large effect on when the loss of load hours occur, but it doesn't have any effect on when the critical hours occur. The critical hours are the hours that are highlighted here, regardless of how storage dispatches. For example, let's pretend that if storage was completely eliminating that first hour of loss of load by discharging more, And so it was no longer a loss of load hour. Well, if you were, and then therefore you'd have larger loss of load on the back end of this event. If you were to add more renewables in that hour, even though it's not a loss of load hour, you would still be improving system reliability because you'd be allowing storage to discharge less in that hour, and then it would have more charge in the tank on the back end that it could discharge to reduce loss of load at the end of this event. So the definition of a critical hour or a critical period is just an hour in which generation actually impacts system reliability or impacts loss of load. And hours in which generation impacts loss of load is not just loss of load hours. It's critical hours. So if you look at the availability of resources during critical hours, that equals marginal ELCC. You sum up the marginal ELCC of all of the resources, you get this bar, and it's in a high renewable, high storage system is going to be less than peak load. So when do these critical hours occur? So this is just highlighting some analysis actually from a report that E3 published many years ago looking at California. If you have a system without any renewables or storage, your critical hours are going to be peak hours, and those are going to occur in the middle of the afternoon. If you add a bunch of solar and storage, you're going to shift those critical hours into the evening, and generally, you're going to also shift them later in the summer. So from June and July towards August and September. And then when you add storage, you're also going to elongate critical periods for the same reasons that Kevin and Nick have both highlighted. So you can see the length of the critical periods in that middle box is slightly longer than in the top box. And then if we imagine a system many decades into the future where we've added tons and tons of solar and storage, as well as other things in the economy like electrification of buildings that are now heated with electricity instead of natural gas, you actually shift the critical periods out of the summer entirely and into winter nights. And at current projections, this is where the California system will be sometime in the 2040s. So not exactly a near-term problem, but eventually winter nights are going to be the challenge in California because we're just going to have so much solar in the summer and so much storage to shift that solar around that the summers, even in the evenings, are not going to be a challenge. It's going to be the winter evenings. So you can take those critical hours that are identified through probabilistic modeling, and you can measure the availability of any type of a resource in that framework that is marginal ELCC, and you can calculate every resource's marginal contribution to system reliability. Do it for solar, for storage, for wind, for batteries, and you can even do it for thermal. And it's increasingly important to do it for thermal for the reasons that Kevin talked about around issues like correlated outage or fuel availability. So every resource can be measured using marginal ELCC, and it's very important from an apples to apples, from a fairness perspective, from an equity perspective, to put all resources on the same level playing field and measure them through a marginal ELCC framework. If you play things out and you look at, well, what happens to every resource's marginal ELCC? You can see there's a general trend that they tend to go down. And that's because as resources saturate the system, their marginal ELCCs decline. And this is particularly true for energy storage, which you can see here, all of the different shades of pink and purple are energy storage and demand response. And this is a forecast, this is a several years out of date illustrative forecast for California, but you can see as energy storage and demand response come onto the system in greater penetrations, their marginal ELCCs decline. Interestingly, if you look at the very bottom bar, that's the yellow bar, that's solar. Solar, if you go back about 15 years in California, also used to be very high. It was about 70%. We've just already crashed solar in California. So that's why you're not seeing a decline, because it's already been declined. And interestingly, what's happening here is that you actually see solar rising in this graph. And that's precisely because of the interactive synergies with storage. Again, what's happening as you add storage onto the system, it's elongating the critical periods from just the net peak into a longer period. And it's actually pushing critical hours back into the middle of the day when solar is available. And solar's then able to take advantage of that and get higher accreditation. And then wind is actually just pretty flat. Wind tends to have very low interactive synergies with other resources because it's just too sporadic. So why is a critical periods framework or a marginal ELCC framework the appropriate accreditation framework? 4 reasons I will posit. Number 1, it ensures reliability. If you can ensure reliability during critical periods, definitionally, you can ensure reliability during all other non-critical periods. And so therefore, it makes sense to focus on critical periods for the purposes of ensuring reliability. Number 2, it's economically efficient. It sends the right signals to both resources and loads. And in fact, loads are just as important here as resources from sending the right signal. And this is an area where Kevin and I have debated many times, and we just agree to disagree on the example that he gave about the solar and it not being, or the storage and it not being economically efficient. But I actually want to talk about loads for a second. If you are in an average ELCC framework, I'm not saying Kevin's advocating for average, but if you are in an average ELCC framework, you are definitionally procuring capacity up to the gross peak, right? If we go back to this graphic right here, the average is definitionally tied to the gross peak, right? If you add up the accreditation of the firm resources, which is the gray, and the renewable resources in this, at their average ELCC, you get the gross peak. And that is also what's called a PCAP framework, or a perfect capacity framework, right? Because if you didn't have any renewables and you only had perfect capacity, you would be procuring capacity, perfect capacity up to the gross peak. Now, what's the problem with this? Problem with this is that it sends an economically inefficient signal to both generators and loads, and in particular loads. In California, which we have this system right here, we have an abundance of energy in the middle of the day during the gross peak. We have time of use pricing programs that are trying to get people to consume more energy in the middle of the day and less energy in the evening. The impact of that is that we are actually intentionally increasing the peak by shifting energy into the afternoon for the benefit of both reliability, because we're shifting energy out of the critical periods and into the peak periods, and for the benefit of the environment, because we have an abundance of clean energy in the middle of the day. So we actually want people to be using more energy during this period, which increases our peak load. And we should not be sending a signal that you will incur higher capacity requirements if you increase your consumption on peak, at least from a generation perspective. Transmission, distribution, that's a whole other story, but from a transmission perspective, I think that's true. It's economically efficient to focus on critical periods. The third reason to move to a marginal ELCC or critical periods framework is that it's technology neutral, which means it's fair and equitable. All resources, and for that matter, all loads, are accredited using the exact same framework. There's no subjectivity around allocation of synergies. which anytime you're doing an average ELCC framework, you inherently have to make entirely subjective decisions around how to allocate a portfolio value. There's no scientifically or mathematically correct way to do that. And fourth, some people might disagree with this, but I think marginal ELCC is very elegant and thus simple. It assigns a singular value to each resource, or for that matter, load on the system, and market participants can plan around that, right? It's much simpler than, for example, a slice of day framework where every resource has 288 values because it has a different reliability value for every hour of every month throughout the year. It's a very fungible product, it's a transactable product, and it's actually a very forecastable product. You can run models and forecast out marginal ELCCs. Now, are they perfectly certain? No, but neither are anything in the energy market. We forecast energy prices all the time. Most of those are wrong, but we do it all the time. And forecasting energy prices from now through 2050, you get, 887, 60 different values per year. With marginal ELCC, you get one value per year. So it's a forecastable product. There are many dozens of models, that loss of load probability models, that can calculate these values. So it is, I would posit, a very industry standard calculation at this point to run marginal ELCCs. And I'll kind of breeze through this just because I think this is less relevant for CAISO, but in a capacity market framework, I think it's important not just to accredit resources, but to hold them financially accountable for showing up consistently with how they've been accredited. Just as a very healthy way to run a market, prevents less gaming, prevents less other bad outcomes, protects loads. And I think this is potentially another area actually where CAISO could improve, right, is on better performance and holding resources accountable. And then this is really just kind of highlighting the simplicity of marginal ELCC or a critical periods reliability framework, just as a singular value for every resource, for every load. Now, if you do something seasonal, then you would have different seasonal values, and there are trade-offs between whether to go seasonal or annual. We could talk about that in Q&A, but I think that covers all the highlights of what I wanted to get to. Any questions?
We have a few questions online. First up, we have Perry.
Hey, this is Perry Servideo, CISA. Thanks for the great presentation. I had a question on slide 111, I think it was. Yeah, so on this one, I'm not sure if it was supposed to be on the chart, but if not, that's fine too. Can you speak to what a marginal ELCC for a natural gas plant in these three different flavors that you have on the right would be? I mean, it's sort of this faded region on the chart on the right, but I'm just like, can you give me a sense on the numbers?
Yeah, we haven't run natural gas or thermal ELCCs for this system. Other ISOs have done that, and it's highly dependent upon the types of risks of the thermal fleet. So if there's a very correlated outage risk, which tends to occur in systems that are subject to really deep cold snaps, or areas that are potentially very fuel constrained, like New England, where all the pipes get full and you just can't get more fuel into the region, and natural gas resources all can't get enough fuel, then you would see a big correlated outage, and natural gas would just be a lower, maybe like 60 to 80% accreditation. And those are the values you roughly see in some of the Eastern RTOs. California is not really subject to those same types of risks. So I would expect the ELCCs for thermal to be slightly higher here. And I will also say that for a system that's very dependent upon thermal, which today, PJM, Texas, New England, they're all very dependent upon thermal, the correlated outage risk matters a lot more. If the role of thermal on the system shrinks, actually the ELCC rises because there's an inherent diversity with the other risks on the system that are driving reliability events like low renewable events. The weather factors that lead to a wind drought, for example, a multi-week wind drought, are not necessarily the same weather conditions that would cause a large correlated outage event on the whole thermal fleet. So it's all a function of what the portfolio is, and you just have to run those calculations.
Yeah, thanks for that. That's really helpful. What's your thought? So am I thinking about this wrong in thinking that, like an ambient outage, an ambient derate due to temperature, is that something that would be in the realm of like what you're calling the correlated outage, or correlated to weather outage? Because that's typically what we would see in the California scenario, is just more ambient outages due to temperature at higher temperatures, which is when they need to run anyway.
Right. Yeah, I think it's just an accounting convention. If you're setting 100% availability based on like a maximum wintertime rating, and then all of the risk is in the summer when you have ambient derates, then yeah, you would be at 90% or whatever the math works out to, right? If you're setting your 100% baseline at the summer already derated value, then your percentage is going to be higher. But ultimately, all that matters is the megawatt output. So I think it's just an accounting.
Yeah, no, that makes a lot of sense. Thanks.
That's also a big issue for demand response. People always get tied up in assigning a percent to demand response. This is a big finding of a demand response ELCC study that E3 did with the CAISO several years ago, with John Good and Lauren Carr and a bunch of others. But it's, saying what the nameplate of demand response is a fool's errand, right? Because it's like, oh, you could say all connected demand response and you have some huge value, but then you have some huge derate. Or you could say the nameplate is like the already derated value, in which case you get a higher percentage. But at the end of the day, the megawatts are the megawatts, and that's what matters.
Next, we have a written question from Andrew Mills asking, on slide 108, if critical periods are not equivalent to loss of load hours, could you repeat how those periods are found or defined?
Yes, that is a great question. So, and I will say, admittedly, outputting critical hours is actually not a standard output of many loss of load probability models. All loss of load probability models output loss of load hours. They don't all output critical hours. So what you have to do is you have to go through and kind of test each hour and say, does an increase in generation or a change in load impact system reliability? That is an intrinsic output of any optimization model. So any loss of load probability model that's run on an optimization base will automatically produce that. But if the loss of load probability model is run through more of a heuristic dispatch, then you'd also have to add a heuristic process to identify the critical hours. So I think a process to do that is an area of research in the industry, but nonetheless, this is meant to tee up the framework and the concept for what critical hours are. Now, the flip side of that, I will say, all loss of load probability models are capable of producing marginal ELCCs. Marginal ELCCs are a very simple calculation, and they inherently only are based on critical hours. So anytime you're running a marginal ELCC, the model is just giving you that value, and it's based on the availability of that resource you're measuring in critical hours, but it doesn't actually require the identification of those hours. So you don't necessarily know exactly when all the critical hours were, but nonetheless, that is what that is based on. And I think that's a very powerful concept, is just understanding that the marginal LCCs are based on availability during critical hours, which is not necessarily loss of load hours, right? Because that's important, right? You know, for what Kevin highlighted earlier, if you have loss of load hours in the evening, it doesn't mean that you might not get some reliability benefit a few hours before that by allowing storage to hold more charge in the tank and then be able to discharge that for those loss of load hours. So that is how solar, for example, is getting, you know, solar is going up here, not because it's discharging during loss of or available during loss of load hours. It's available because it's allowing storage to delay its discharge later in the evening and be able to reduce loss of load later in the evening.
Can you re-explain that? Because so you said you run your loss of load expectation analysis and you identified some critical hours. And then you define your counting methodology using the marginal ELCC for those identified hours. Is that correct? More or less?
You can do it a couple of different ways. So one way to accredit resources under the framework that I'm proposing is to, you know, run hundreds of years, identify the critical hours within that very long data set, and then look at the availability of resources during those critical hours. Or you could just, you know, have us do the calculation that Kevin and Nick have described, which is just more traditional marginal ELCC calculation, which all you do there is you have a starting system with a set level of reliability, you add a resource to it, any resource, right? Renewable, storage, thermal, anything. Anytime you add a resource to the system, doesn't matter what it is, the reliability of the system is going to get better because you're adding more capability. And then that allows you to remove perfect capacity from the system. And the quantity of perfect capacity that's removed is the marginal ELCC of the resource that you added. That is traditionally the way that marginal ELCCs are done. And that is almost certainly a simpler method than the identification of critical hours. But conceptually, they are the same thing.
Second question is more like, do you have any correlation between those hours?
What do you mean correlation?
I just try to, because you define your critical hours. I was just wondering, with the marginal principle you were explaining, like if you identify in the analysis you have been doing, like some correlation between hours, like the fact that you are critical at hour 7, how is it related to the fact that you can be critical at hour 23, or does it not relevant at all?
Yeah, I'm not really sure that there's necessarily a great way. And the other thing is, this is a, you know, one illustrative day, but in reality, what this is based on is a like 1,000-year hourly data set, and critical hours will just pop up whenever they pop up. Some days they'll pop up for 1 hour, some days they'll pop up for 8 hours. 99.9% of the days they won't pop up at all. So it's just they pop up when they pop up, and then you look at the availability of resources during those hours.
In the interest of time, we only have time for one more question.
I'll probably go ahead and jump in because I'm probably the devil's advocate here. Doug Carpa, Peninsula Clean Energy. I wanted to thank you actually for doing a great case for slice a day here, because I think one of the things I come away with is that both average and marginal ELCC are kind of trash, in the sense that, so I'll start here with this slide. I told you I was going to be the devil's advocate, right? Actually, could I go to, let me start with, now that I'm done being provocative, slide 111. And I think the thing that I keep coming back to is the statement that you said that like, it depends, you have a starting system, which in all ELCC, you start with like what exists on the grid, and then you start backing out resources. Well, you've already changed the ELCC as soon as you've done that, because it's the partial derivative of reliability with respect to the set of resources. Depending on what you back out, you're going to have shifts, as this slide shows, right? If you were to start like, we're going to take all the thermal out and replace it with solar, well, you're going to have different ELCCs. And when we do RA showings, that's exactly what we're doing. because ahead of time, we don't know what's under RA contract. And so it could be that the monthly showings are going to have way more solar than you thought, or maybe it's going to be way more thermal than you thought. But no matter what happens in the RA program, you're going to be you're unable to predict what precise set of resources are going to show up, which means the actual appropriate ELCC is an unknown. And so it's sort of a little bit that thing of like, not only does God play dice, but he throws them where they can't be seen. Because from an LSE perspective, and possibly also from the ISO perspective, you might get, if you're going through that exercise of like, can we run the system based on only what's under RA contract? If it's really thermal heavy, maybe you've got more ELCC value. If it's really solar and wind heavy, then it's going to be maybe less reliable, but you won't be able to tell because you're using this kind of highly derivative construct. And I think to illustrate the point a little bit further, if you want to go back to 108, this is actually a great example of how we got to slice a day, because if you're looking at this period from like 17 through 23, and you're like, okay, this is the critical hours. And it's like, it's great to be able to focus on those hours. But the problem that you end up with here is you've got this single metric, right? Which isn't really appropriate for a system where things are varying over time. Like fundamentally, things are varying over time. And so you have your stack here on the right, but half of your hours, you're under the mark. And half your hours, you're over the mark, right? So if you are in, you've gone out and you're showing RA relative to, that average across those hours. Well, in 18, 19, and 20, you're going to be short. And if load stays high later than you expect, you can have an outage, which I think is kind of what we had in 2020. And so you look at that and you think, well, okay, well, maybe we do need to keep track of the early part of the critical hours and the late part of the critical hours. And then you're like, okay, well, what about every hour? And then you're in slice of day mode. And the last point, so this is sort of food for thought, but I just thought somebody should stand up and put the plug in for a slice a day. But the last part that I really wanted to emphasize is a bit of the equity piece, because one of the reasons PCE in particular was, went in for slice of day is because we are not getting to that 100% renewable grid in 2040. We're doing it 2028, 2029. So we're already in that future, or very, very close to it. And one of the problems ELCC has is those values, the values of our portfolio. It may be capable of serving our customers in every hour, but the value of it depends on what everybody else is doing. So if everybody else is holding on to their gas, our ELCCs are artificially depressed. We now have to go out and procure extra resource, not to supply our load, but to supply theirs. And that is a cost shift. And that's part of the reason why the idea of you have resources, solar does what it does in every hour, we can describe that. It is fixed. It's going to be the same thing in 2050 that it is today, because physics is physics. Same for wind, same for everything else. If those values are fixed, if the accreditation is fixed, then we know the value of our portfolio. And if we can bring resources that meet our load, we're good. And then what everybody else is doing can shift around that. And then what
Thank
ends
you
up,
for your comments. I'm so sorry, but we
yeah,
need
that's
to
probably it.
continue
I'll just
on.
stop there. Anyway, some food for thought, because I wanted to get to it because we don't have much time.
Yeah, we should probably continue on to the
And now you don't have any
next
time to respond.
presentation.
I'm sorry, Zach. We can talk.
I will just respond to the last part. Otherwise, I'd be responding for another 15 minutes. The last point about you procuring capacity for other entities, I think is not true. What a marginal ELCC construct does, for all a marginal ELCC construct does is, depending on what's happening on the rest of the system, the critical hours are shifting around. So the critical hours could be in the peak hours, they could be in the evening, they could be in the morning. It just completely depends, you're right, on what everyone else is doing. But for any individual load serving entity, all a marginal ELCC framework is doing is saying, do you have resources during the system critical hours to cover your load during the system critical hours? If you have that, then you will be reliable. You're completely immune to the shifting values. All that matters is, can you cover your own load during those critical hours, and it will stack up.
Thank you.
Thank you so much, Zach. Sorry, Steve, we couldn't get your question. Hopefully you can catch Zach. And the next presenter is Bedad. Please let us know and we'll be happy to adjust the slides from our side.
Good afternoon, everyone. My name is Bedad Kiani. I'm a senior analyst at working with the Energy Resource Modeling Group at California Public Utilities Commission. And I would go through our work on reliability modeling, an overview of our study process we had in 2024. Next slide, please. So we have two objectives for LOLE studies at CPUC. We have a near-term study for RA, and we have a long-term study for IRP purposes. And for the RA, we conduct annual and monthly loss of load expectation studies. Any questions? Okay, so for the annual and monthly loss of load expectation, we did it for 2026 with some recent model updates to determine the 0.1 LOLE, which is equivalent to one loss of load event in 10 years. For our long-term study, which is done for the IRP group, we do the long-term annual LOLE modeling to inform the IRP proceeding, such as the preferred system plan we completed at the end of 2023, or the CAISO transmission planning process, or the TPP portfolio will be completed end of 2024. Next slide, please. So our outline for reliability assessment, we have a near-term, a mid-term, and a long-term assessment. We perform the near-term for RA purposes. It's 1 to 3 years out. We have mid-term assessment, which is mostly for IRP. It's 6 to 10 years out for the LSE procurement planning, and we have a longer term, 10 to 15 year out, which is conducted for transmission planning purposes mostly. Next slide, please. So our studies timeline and results, our current CPUC modeling data set, which can be found at the link that you would find it in the slides. The results, we had an RA proceeding, R23-10-011. We had a July 25, 2024 presentation by staff. We presented the primary results for the July 2024 loss of load expectation study, which was a study targeted for 2026. On August 30th, an appendix was published with updated results, which again, we are providing the link here and the SOD tool link. We have, upon feedback of stakeholders, a revised study to be published early December, followed by a workshop later in the December for further stakeholder comments. For IRP proceeding, in November, we have we will test the reliability of portfolios for use in CAISO's 2025-26 TPP planning. And in quarter one of 2025, we will refresh the reliability and ELCC calibration between Resolve and SERVM models in preparation for establishing the LSE filing requirements. Next slide, please. So our current RA near-term 2026 LOE study, we are providing some regarding the reliability requirements, we have compared the prior RA study, which was done in early 2023, which we had targeted the year 2024 in that study, and the current LOA study, which is released mid-2024, and the revision would be released, as I explained before, in December 24, which we are showing a lower reliability requirement to achieve a 0.1 event per year. Initially, the study revealed an over-reliable system, a loss of load less than 0.1, which required tuning to surface reliability events. That means we tuned the reliability by import constraints, reducing the constraint, which was originally set to 4,000 megawatt in critical hours, to 2,500 megawatt, instead of removing the existing units. The key factors change that driving the reliability outcome was, first of all, we had the recent results showing lower requirements, largely due to tuning the model to match the lower hyper demand forecast for 2023 hyper based on the managed peak related to 2021, which was based on the consumption hyper in the previous study. Additionally, in 2022, in our recent study, the 2022 weather year distribution was added, which is providing a more extreme weather trends to increase reliability need. And this factor has increased the reliability need for our study, a recent study. We have updated unit outage rates and ambient temperature output rating, which tends to increase the reliability need as well. So there are the key factors that have changed the reliability needs in the recent study. And similar to KAISU scenario 3, our results are compared. Our current 2026 study resembling the short-term scenario 3 of KAISU study, which uses all available RA capacity, not just contracted or minimum requirement capacity levels. And our model has a small capacity surplus in 2026, given inclusion of expected in-development projects in the updated baseline. Next slide, please. So for the RA methodology and slice of day framework, we have this schematic diagram, which I would briefly explain how it works. Initially, we have an annual loss of load study baseline. If LOL is larger than 0.1, we add a perfect capacity until we reach we achieve a LOLE that is equal to or smaller than 0.1. If loss of load was smaller or equal to 0.1, we would proceed to the next step. So if it's actually less than or equals 0.1, we calculate the PRM for peak based on the 0.1 LOLE, apply the peak month PRM across all months, and if LOLE is still smaller than 1, the peak PRM will be adopted. If not, assess LOLE and conserved energy, adjust annual PRM until we solve for the 0.1 LOLE. On the other hand, on the right side, we apply the stress tests to rate the monthly PRM level for each month of the year. We test the minimum level of reserves needed in each month of the year by doing the monthly loss of load study. So next slide, please. Here we are explaining the IRP reliability study framework, which we process using the capacity expansion model resolve and the LOLE model SERVAM to project optimal resource portfolios in the mid and long term, which will meet the reliability requirements as well as the GHG reduction and other policy objectives. So these two models, the way they interact, we first find the results from the SERVAM upstream calculations. We find the total reliability need and perfect capacity planning reserve margin and the ELCC values for our resource classes, introducing curves and surfaces, etc. We run the result portfolio, we build a result portfolio, which with our stakeholder E3 help, which expands the portfolio to meet PCAP, PRM, counting reliability contribution using SERVAM-derived ELCC values. And then we check this portfolio through a run of SERVAM for the reliability check. We check the if it's against the 0.1 LOLE target. We calculate the PCAP, required PCAP, or as needed, or if we have a surplus or shortfall of PCAP, we calibrate it, and then as needed, we iterate it with the resolve runs. And this iteration would take place until we achieve a reliable system and an optimized system in the long run energy planning. So this was the a brief explanation of what we are doing at CPUC. And I believe this is the last slide. If any questions, we would be happy to answer your questions with Donald Brooks, which is our supervisor. Thank you.
Thank you. Are there any questions? Okay, over to you, Aditya.
Thank you so much, Vedad.
Thank you.
Right, next slide, please. All right, so we have the last 6 minutes for today's, and I know it has been a lot of discussion on the RA space yesterday and today. I really appreciate our presenters from external, Evan, Zach, Nick, Vedad. Thank you so much. It gives different perspectives from across the environment for us to look at. As we think about this thing, I would appreciate if you guys give me your feedback and input on what the ISO should be thinking about in the default rules and default PRM calculations. I subscribe to some of the philosophy that was shared by some presenters. It needs to be easy to calculate. It shouldn't change a whole lot year to year. It should have some level of forward visibility and consistency. That's where our midterm and long-term analysis will help guide us. So suddenly seeing a lot of swings is not necessarily useful. And some of those philosophies have to be taken into consideration in the development of these numbers. Many years ago, when we were trying to do loss of load modeling and calculating PRM, as the numbers changed from year to year, we were required to show what variable changes and how much that impact was from a waterfall standpoint, basically to communicate. Because if somebody uses those, I mean, at that point, they were all using that numbers, but it costs millions of dollars to get additional capacity. What does it mean? Show me the drivers and all of that vetting process. But in this space where we are, and the default rules should be something that we all can apply and use, and at least for those LSEs, LRAs that defer to using the default rules, we should have some easy to apply, easy to understand, easy to follow kind of framework. Easy to calculate, I'm not too much because we can do the work, but it should be easy to apply. So we are asking 4 generic questions. Any final thoughts on inputs and assumptions changes? After December 10th, we will start putting stuff into our models, so we'll have less ability to adjust after that. I mean, if you come back to us in January, so that'll be nice to have your inputs there. Any preliminary suggestions on midterm and long-term data that you guys seen, that will be useful. And the more importantly, I'm trying to get your feedback on capacity accreditation methods. Which of the many approaches that you guys see today resonate with you, which we should consider. Don't have the ability to explore with all the methods and creating a bunch of PRM numbers. That is not useful. We want to kind of align in one direction and kind of march and run. And anything else that you would like to say? I seriously, I really appreciate the way you've provided feedback last time based on my request. Bolded sentence with what you want us to do, and then supporting material. It doesn't have to be long, just brief sentences is enough. And if we need more information, we'll come back to you and ask. So makes your life easy, makes our life easy. What else? You have time until December 10th. Granted that next week is Thanksgiving, so we gave you more time. So Ansel doesn't come back and ask me more time. So that's there. You can do the same thing. If you have any specific questions and would like to sit down and talk to us, we're happy to chat. And any questions, you can reach out to me or any of the members of my team. And thank you so much for another productive session today. You all have a wonderful evening. Thanks.
Thank you so much for joining today's discussion. As a reminder, this meeting is recorded for informational and convenience purposes only. The video file will be posted on the initiative webpage. Thank you. We hope you have a wonderful rest of your day.